Time in physics enters the theory through measurement rather than assumption. Its meaning is established operationally by specifying procedures that produce numerical readings from physical systems. In this framework, time is defined by clocks, and every statement about time must ultimately be reducible to a statement about the behavior of real physical devices that function as clocks. This operational definition anchors time firmly in experiment and removes it from the realm of abstract background parameters. A clock is any physical system that exhibits a stable, repeatable process whose evolution can be counted or compared. A pendulum completes swings, a quartz crystal vibrates, an atom undergoes electronic or hyperfine transitions, and an unstable particle decays with a well-characterized probability distribution. Each of these processes can be used to construct a clock, provided the process is sufficiently regular and insensitive to uncontrolled environmental disturbances. What unifies these diverse systems is not their internal mechanism, but their capacity to mark intervals through reproducible change. This operational stance distinguishes modern physics from everyday intuition. In ordinary experience, time appears uniform and universal. All clocks seem to agree, and their agreement is rarely questioned. Classical mechanics formalized this intuition by introducing time as an external parameter that advances identically for all observers, independent of motion or location. In that picture, clocks simply reveal an already existing temporal flow. Precision measurement transformed this picture. As clock technology advanced, it became possible to compare clocks under conditions involving motion, transport, and varying environments. These comparisons revealed systematic reproducible differences between clocks that could not be attributed to mechanical imperfections or environmental noise. The role of theory shifted accordingly. Instead of assuming a universal time and treating clocks as imperfect indicators, physics began treating clocks as the primary realizations of time itself. This shift introduces a crucial distinction between proper time and coordinate time. Proper time refers to the time measured by a clock along its own physical trajectory through space-time. It is local and intrinsic to the clock. Coordinate time is a parameter assigned by a chosen reference frame to label events throughout space. It serves as a convenient organizational tool for describing extended systems, but it is not directly measured by any single clock. Operationally, proper time holds a privileged position. A clock directly measures its own proper time by counting cycles of its internal process. No synchronization with distant clocks is required. No assumptions about signal propagation enter the definition. If a clock records a certain number of oscillations between two events on its world line, that count defines the elapsed proper time for that clock. Coordinate time arises from the practical need to compare events occurring at different locations. To define coordinate time experimentally, many clocks must be distributed throughout space and synchronized according to a specified procedure. A common method uses light signals exchanged between clocks under the assumption that light propagates at a constant speed in the chosen frame. This procedure is operational and reproducible, but it depends on conventions and assumptions that must be stated explicitly. The difference between proper time and coordinate time becomes physically significant as soon as motion enters the problem. When all clocks remain at rest relative to one another, their proper times advance at the same rate, and the distinction remains hidden. Motion breaks this symmetry. Clocks following different trajectories accumulate different amounts of proper time, even if they start synchronized and later reunite. This divergence is an empirical fact. Two identical clocks can be synchronized, subjected to different motions, and then brought back together for direct comparison. When placed side by side, any difference in their readings reflects a difference in the proper time accumulated along their respective paths. The comparison requires no interpretation and no correction for signal delays. The clocks simply disagree, and the disagreement is reproducible. Motion forces time to become measurable rather than assumed because it demands comparison. Comparison requires physical operations, transporting clocks, exchanging signals, or reuniting devices after separation. Each operation generates data. These data constrain theory and give time a concrete experimental meaning. The operational importance of proper time rests on the observed universality of clock behavior. Atomic clocks based on different transitions, optical clocks operating at vastly different frequencies, particle decay processes, and macroscopic oscillators all exhibit the same relativistic dependence on motion within experimental uncertainty. This universality indicates that time dilation reflects a property of space-time itself, rather than the response of specific mechanisms. This conclusion emerged from experiment rather than assumption. Early investigations considered the possibility that different clocks might respond differently to motion. If time dilation depended on internal structure, it would lack fundamental significance. Experimental results instead demonstrated that once non-relativistic effects such as temperature variation, acceleration-induced stress, and electromagnetic interference are controlled, all clocks respond identically to velocity. This empirical consistency elevates proper time to a central physical quantity. Proper time can be expressed mathematically as an integral along a world line, but its operational meaning remains straightforward. It is the time recorded by a clock carried along that path. The mathematical expression encodes the behavior of clocks. It does not define time independently of measurement. The logical direction runs from experiment to formalism. Coordinate time remains indispensable for practical calculations. Describing the motion of many bodies, writing conservation laws, and formulating field equations all benefit from a shared temporal coordinate. The physical content of coordinate time, however, derives entirely from its relationship to proper time through synchronization procedures and motion-dependent corrections. Synchronization itself is an experimental process. Two distant clocks cannot be compared instantaneously. Signals must be sent and received, and delays must be accounted for. In special relativity, the standard synchronization convention uses light signals exchanged symmetrically between clocks. This convention reflects extensive experimental evidence regarding the propagation of light and yields consistent results within inertial frames. While synchronization conventions affect coordinate time assignments, they leave proper time unchanged. A clock's accumulated proper time remains the same regardless of how coordinates are defined. This invariance gives proper time a robustness unmatched by any global temporal parameter. The experimental relevance of this distinction becomes clear in systems involving high velocities. Particle lifetimes measured in laboratories depend on the proper time experienced by the particles, not on the laboratory's coordinate time alone. Oscillation frequencies in atomic transitions shift with velocity in precisely the manner predicted by relativistic time dilation. Phase accumulation in interferometric experiments depends on the proper time along each path. These effects translate directly into counting experiments. The number of decay events observed, the number of oscillations completed, or the accumulated phase difference between two paths all provide measurable quantities. Relativistic time dilation manifests as a difference in these counts when systems follow different trajectories. The operational definition of time also clarifies simultaneity. Events described as simultaneous require synchronized clocks at different locations. Because synchronization depends on the observer's state of motion, simultaneity becomes frame-dependent. This dependence arises from the physical behavior of clocks and signals rather than from interpretive choices. Time dilation, viewed operationally, concerns rates and counts rather than perception. A moving clock completes fewer cycles than a stationary one during a given interval of coordinate time defined in a chosen frame. This statement maps directly onto experimental procedures. Count cycles, compare clocks, and analyze discrepancies. The effect does not rely on mechanical slowing or forces acting on clock components. It appears in inertial motion, where no force acts on the clock. It persists when clocks are reunited and compared locally. It applies uniformly across clock technologies. These features distinguish relativistic time dilation from classical perturbations. Modern time standards reflect this operational foundation. The definition of the second specifies a fixed number of cycles of a particular atomic transition. National and international timescales are constructed by comparing ensembles of atomic clocks and averaging their behavior. Motion-dependent corrections are applied explicitly when clocks move or reside at different gravitational potentials. In practical terms, the operational meaning of time underpins technologies that rely on precision timing. Satellite-based navigation systems, high-speed communication networks, and fundamental physics experiments all depend on accurate modeling of proper time and its relationship to coordinate time. These applications succeed because the behavior of clocks under motion is well understood and experimentally verified. Motion therefore plays a decisive role in revealing the physical nature of time. It exposes differences between local measurements and global descriptions. It forces the comparison of clocks and transforms time from an implicit parameter into an observable quantity subject to experimental test. By grounding time in clocks and their behavior, physics treats time as a measurable aspect of physical reality. Proper time provides the invariant measure along individual histories, while coordinate time organizes descriptions across space. Experiments with moving clocks do not merely illustrate theoretical ideas, they establish the operational meaning of time itself. Relativistic time dilation emerges directly from the structure of space-time implied by the laws of electrodynamics and the empirical behavior of light. Its foundation lies in the requirement that the speed of light in vacuum takes the same value for all inertial observers, independent of the motion of the source or the observer. This empirical fact, established by a wide range of optical and electromagnetic experiments, forces a precise mathematical relationship between the space and time coordinates used by different observers. That relationship is encoded in the Lorentz transformations. The Lorentz transformations arise from two experimentally grounded principles. The first states that the laws of physics take the same form in all inertial reference frames. The second states that light propagates in vacuum at a fixed speed that does not depend on the motion of the emitting source. Together, these principles restrict how measurements of space and time made in one inertial frame relate to those made in another, moving at constant velocity relative to the first. Consider two inertial frames, each equipped with identical rulers and clocks. One frame is designated as the reference frame and the other moves at a constant velocity along a straight line relative to it. Each observer assigns coordinates to events using their own clocks and rulers. The problem is to determine the transformation rules connecting these coordinate assignments while preserving the experimentally observed invariance of the speed of light. Light propagation provides the key constraint. In each inertial frame, a spherical wavefront emitted from a point source expands outward at the same speed. The equation describing this expanding wavefront must take the same form in both frames. Classical Galilean transformations fail to satisfy this requirement because they predict different light speeds in different frames. The Lorentz transformations are the unique linear transformations that preserve the light cone structure of spacetime while satisfying the principle of relativity. These transformations mix space and time coordinates in a velocity-dependent way. Time intervals measured in one frame depend on both time and space intervals measured in another. This mixing is not a mathematical curiosity, it reflects how clocks and rulers behave when set in relative motion. From the Lorentz transformations, time dilation follows as a direct consequence. Consider a clock at rest in one inertial frame. In that frame, successive ticks of the clock occur at the same spatial location, separated only by a time interval. When these same events are described in a frame moving relative to the clock, the events occur at different spatial locations as well as different times. The Lorentz transformation relates these coordinates and shows that the time interval between ticks measured in the moving frame is longer than the proper time interval measured by the clock itself. This result introduces the concept of kinematic time dilation, which depends solely on relative velocity. The factor by which time intervals are dilated is determined by the Lorentz gamma factor, which depends on the ratio of the relative velocity to the speed of light. As velocity increases, the gamma factor increases, and moving clocks accumulate less proper time compared to clocks at rest in the chosen frame. Kinematic time dilation arises entirely within special relativity. It requires no gravitational fields, no acceleration, and no reference to space-time curvature. The effect applies to inertial motion and follows from the geometry of flat space-time. Its experimental verification relies on measurements involving relative motion alone, such as high-speed particles, transported clocks, or rotating systems analyzed locally. A clear separation between kinematic and gravitational effects is essential. Gravitational time dilation arises from differences in gravitational potential and is described by general relativity. Although both effects alter clock rates, their physical origins differ. Kinematic time dilation results from relative velocity and the structure of space-time under Lorentz symmetry. Gravitational time dilation results from space-time curvature produced by mass energy. This separation is not merely conceptual, it is operational. Experiments can be designed in which gravitational effects are negligible and velocity effects dominate. Conversely, experiments can isolate gravitational effects with minimal relative motion. In practice, many real-world systems involve both contributions, requiring careful accounting of each. The mathematical form of the Lorentz transformations also clarifies the limits of classical simultaneity. In classical physics, simultaneity is absolute. If two events occur at the same time in one frame, they occur at the same time in all frames. This assumption rests on the idea that time is universal and independent of motion. Relativity replaces this assumption with an operational definition of simultaneity based on synchronized clocks. Synchronization requires a procedure typically involving the exchange of light signals. When clocks are synchronized in one inertial frame using such a procedure, they define simultaneity within that frame. Another inertial frame moving relative to the first employs its own synchronization procedure, which leads to a different assignment of simultaneous events. The Lorentz transformations quantify this effect precisely. Two events that share the same time coordinate in one frame generally occur at different times in another frame moving relative to the first. This relativity of simultaneity follows inevitably from the invariance of the speed of light and the operational nature of clock synchronization. The breakdown of absolute simultaneity has direct consequences for time dilation. The rate at which a moving clock appears to run slow depends on how events along the clock's world line are compared to events in the observer's frame. These comparisons rely on simultaneity conventions, which differ between frames. Time dilation thus reflects both the geometry of space-time and the operational definition of time coordinates. Despite this frame dependence, proper time retains an invariant status. The proper time between two events on a clock's world line depends only on that world line and not on the coordinate system used to describe it. All inertial observers agree on the proper time accumulated by a clock between two events, even though they may assign different coordinate times to those events. This invariance provides a unifying thread between special and general relativity. In flat space-time, proper time depends on velocity. In curved space-time, proper time depends on both velocity and gravitational potential. In both cases, the clock's reading defines the physically meaningful elapsed time. The geometric interpretation of the Lorentz transformations offers further insight. Space-time can be represented as a four-dimensional continuum with a metric that encodes the invariant interval between events. This interval combines spatial separations and temporal separations in such a way that its value remains the same for all inertial observers. Proper time corresponds to the interval measured along a time-like path. Within this geometric framework, time dilation emerges naturally. Different paths between the same pair of events correspond to different amounts of proper time. A clock following one path accumulates a different elapsed time than a clock following another, even if both start and end together. Relative velocity determines the shape of these paths in space-time and therefore the accumulated proper time. This interpretation underscores that time dilation is not a dynamical effect acting on clocks. It reflects the structure of space-time itself. Clocks do not slow down because of mechanical stress or signal delays. They record different amounts of proper time because their world lines differ. The distinction between kinematic and gravitational time dilation becomes especially clear in this geometric language. Kinematic effects arise from the tilt of world lines in space-time diagrams representing relative motion. Gravitational effects arise from curvature that alters the metric itself. Both influence the length of time-like paths, but through different mechanisms. Experimental tests of relativistic time dilation rely on this theoretical foundation. Predictions derived from the Lorentz transformations specify how clock rates depend on velocity. These predictions can be compared directly with measured frequency shifts, decay rates, or accumulated time differences. The agreement between theory and experiment across a wide range of velocities confirms the validity of the Lorentz symmetry underlying special relativity. The limits of classical simultaneity and the emergence of time dilation also impose constraints on how physical laws are formulated. Equations that treat time as an absolute parameter fail to remain invariant under Lorentz transformations. Modern physical theories therefore adopt formulations that respect relativistic covariance, ensuring that predictions remain consistent across inertial frames. In practical terms, this foundation guides the interpretation of experiments involving moving systems. When clocks move relative to a laboratory, their readings must be compared using the Lorentz transformations. When particles move at relativistic speeds, their internal processes evolve according to proper time rather than laboratory time. These considerations are not optional corrections, they are central to accurate modelling. Relativistic time dilation thus rests on a tightly connected set of principles: the invariance of the speed of light, the operational definition of time through clocks, the Lorentz transformations relating inertial frames, and the abandonment of absolute simultaneity. Together, these elements form a coherent framework that replaces classical intuitions with experimentally grounded relationships. Within this framework, time becomes a measurable quantity tied to motion and geometry. The foundations laid by the Lorentz transformations provide the theoretical structure that experiments with moving clocks continually test and confirm. Early investigations into time dilation unfolded long before technology allowed clocks to be transported at high speed or compared with modern precision. During this period, the concept of time dilation was approached indirectly through reasoning based on electromagnetic theory, the behavior of unstable particles, and carefully constructed thought experiments. These early conceptual tests did not rely on precision timekeeping devices in the modern sense. Instead, they used physical processes whose temporal behavior could be inferred from statistical regularities, symmetry arguments, and consistency with known laws of physics. At the turn of the 20th century, the dominant framework for understanding time was classical mechanics. Time was treated as an independent parameter, advancing uniformly and identically for all observers. This assumption worked well for everyday phenomena and for most laboratory experiments. Difficulties emerged when classical mechanics was combined with Maxwell's equations of electromagnetism. Maxwell's equations predict a fixed propagation speed for electromagnetic waves in vacuum, a speed determined solely by fundamental constants. Classical kinematics, which allowed velocities to add linearly, conflicted with this prediction. Attempts to reconcile this conflict initially focused on modifying the behavior of light rather than time. Hypotheses involving a stationary luminiferous medium were introduced to explain why the speed of light appeared constant in many experiments. The failure to detect motion relative to such a medium forced a deeper reconsideration of the assumptions underlying space and time themselves. Before clocks could be flown around the Earth or placed on satellites, time dilation appeared first as a theoretical necessity. Thought experiments played a crucial role in clarifying its implications. One of the most influential conceptual tools was the light clock. A light clock consists of two mirrors facing each other, with a pulse of light bouncing back and forth between them. Each round trip of the light pulse defines one tick of the clock. The light clock is powerful because its operation depends directly on the propagation of light. In the rest frame of the clock, the light travels vertically between the mirrors, covering a fixed distance at a fixed speed. The tick interval is simply the distance divided by the speed of light, multiplied by 2. This defines the proper time between ticks. When the same light clock is observed from a frame in which the clock is moving sideways, the situation changes. The light pulse still moves at the same speed, but it follows a longer diagonal path between the mirrors. Because the speed of light remains fixed, the longer path requires more time to traverse. As a result, the moving clock ticks more slowly than an identical clock at rest in the observer's frame. This reasoning requires no assumptions about mechanical clocks or material processes. It relies only on the invariance of the speed of light and basic geometry. The conclusion is unavoidable within those assumptions. Any clock whose operation depends on light propagation must exhibit time dilation when moving. The light clock argument gained importance because it suggested that time dilation was not an artifact of specific clock mechanisms. If even an idealized clock based on light itself experienced time dilation, then the effect had to be rooted in the structure of space-time rather than in the imperfections of devices. Parallel to these conceptual developments, physicists were studying unstable particles produced by radioactive decay and cosmic radiation. Long before atomic clocks, particle decay offered a natural time scale. The decay of unstable particles follows a characteristic statistical pattern described by a mean lifetime. This lifetime is measured by counting decay events as a function of time and fitting an exponential decay law. In the rest frame of the particle, the mean lifetime is a fixed property determined by the underlying interaction. If the particle moves at high speed relative to the laboratory, classical reasoning predicts that the lifetime should remain unchanged, since time is assumed to be universal. Relativistic reasoning predicts a different outcome. The moving particle's internal processes evolve according to its proper time, while laboratory measurements are made in coordinate time. The relationship between these times implies that the particle should appear to live longer when moving at high velocity. Early particle experiments provided suggestive evidence for this effect. Electrons emitted in beta decay, for example, reached velocities close to the speed of light. Theoretical calculations of their behavior, including energy loss and interaction rates, were consistent only when relativistic corrections were applied. Although direct lifetime measurements at that stage lacked high precision, the consistency of relativistic predictions across different phenomena strengthened confidence in the underlying framework. Cosmic rays provided another natural testing ground. High-energy particles originating outside the Earth's atmosphere were observed at the surface, despite having rest frame lifetimes too short to survive the journey under classical assumptions. The most striking example involved muons produced in the upper atmosphere. Classical reasoning predicted that most muons should decay long before reaching ground level. Observations showed otherwise. Before dedicated experiments quantified this discrepancy precisely, the qualitative conclusion was already clear. The survival of fast-moving, unstable particles over long distances required an explanation involving time dilation. The particles' internal clocks were effectively running more slowly relative to the Earth-based frame. These particle-based arguments were particularly compelling because they did not involve mechanical clocks at all. The decay process itself served as a clock. Each decay event marked the end of a particle's lifetime, and the statistical distribution of decay times provided a measurable quantity. The agreement between observation and relativistic predictions suggested that time dilation applied universally, even to subatomic processes. Thought experiments extended these insights further by examining the consequences of time dilation for synchronization and simultaneity. Classical simultaneity assumed that events occurring at the same time for one observer occurred at the same time for all observers. Operationally, simultaneity depends on synchronized clocks at different locations. Synchronization requires a procedure, and that procedure involves signal propagation. By analyzing synchronization using light signals, early relativistic reasoning showed that simultaneity could not be absolute if the speed of light was invariant. Two observers in relative motion would disagree on whether distant events occurred simultaneously. This conclusion followed directly from the same assumptions that led to time dilation. The interdependence of time dilation and the relativity of simultaneity became evident through these conceptual analyses. Time dilation was not an isolated effect, but part of a broader restructuring of temporal concepts. Without precision clocks, these conclusions rested on internal consistency and empirical constraints from electromagnetism and particle behavior. The theoretical framework synthesizing these ideas was articulated most clearly by Albert Einstein. His formulation of special relativity replaced the assumption of absolute time with operational definitions grounded in measurement and synchronization. The theory did not introduce time dilation as a hypothesis to be tested later. It derived time dilation as a necessary consequence of two empirically motivated postulates. The absence of early precision clocks did not weaken the argument. On the contrary, it forced reliance on diverse physical phenomena. Light propagation, particle decay, and electromagnetic interactions all pointed toward the same conclusion. Time behaved differently for systems in relative motion. This convergence was crucial. If time dilation had appeared only in abstract thought experiments, it might have remained speculative. The fact that independent lines of reasoning, grounded in different areas of physics, all required the same modification of temporal concepts gave the theory credibility before direct clock experiments were possible. The pre-atomic clock era also highlighted the importance of universality. Time dilation affected light clocks, decay processes, and electromagnetic interactions in the same quantitative way. This universality suggested that time dilation was not tied to specific forces or materials. It reflected a deeper symmetry of nature. As experimental techniques improved, these early conceptual insights guided the design of laboratory tests. Particle accelerators, transported clocks, and later atomic and optical clocks provided increasingly precise confirmations. The early reasoning determined what to measure and how to interpret the results. In retrospect, the period before precision clocks played a foundational role in establishing the meaning of time dilation, by forcing physicists to rely on operational definitions, consistency arguments, and indirect evidence. It clarified that time dilation was a property of physical law rather than an artifact of instrumentation. These early conceptual tests transformed time from an assumed background parameter into a measurable quantity tied to motion. They demonstrated that even without sophisticated clocks, the structure of space-time could be inferred from the behavior of light and matter. The later experimental era did not overturn these conclusions. It refined and quantified them. The path from thought experiment to laboratory verification illustrates a central feature of modern physics. Deep, conceptual reasoning, grounded in empirical constraints, can reveal aspects of reality long before technology catches up. In the case of time dilation, the absence of precision clocks sharpened the argument and laid the groundwork for one of the most robustly confirmed predictions in physics. Mon lifetime experiments in the atmosphere provided one of the earliest and most compelling direct demonstrations of relativistic time dilation using naturally occurring particles. These experiments rely on the production, propagation, and decay of muons generated by cosmic radiation and measured at different altitudes. The The results establish a quantitative link between the rest frame lifetime of an unstable particle and the extended lifetime observed in the laboratory frame when the particle moves at relativistic speed. Muons are elementary particles belonging to the lepton family. They carry the same electric charge as electrons, but possess a much larger mass, approximately 207 times greater. Muons are unstable, decaying primarily into an electron and two neutrinos through the weak interaction. In the muon's rest frame, the decay process follows an exponential law with a well-defined mean lifetime of about 2.2 microseconds. This lifetime is measured in laboratory conditions by producing muons at low velocity and recording the time distribution of their decay products. The relevance of muons to atmospheric experiments arises from their natural production in the upper atmosphere. High-energy cosmic rays, composed primarily of protons and heavier nuclei, continuously strike Earth's atmosphere at relativistic speeds. When these primary cosmic rays collide with atomic nuclei in the upper atmosphere, they initiate cascades of secondary particles. Among these secondary products are pions, which themselves are unstable and decay rapidly into muons and neutrinos. Pion decay occurs at altitudes typically ranging from several kilometers to tens of kilometers above Earth's surface. The muons produced in these decays inherit large velocities, often exceeding 0.99 times the speed of light. At such speeds, their kinetic energies are sufficient for them to travel long distances through the atmosphere before decaying, provided relativistic effects are taken into account. A simple classical estimate highlights the problem these experiments address. In the muon's rest frame, the mean lifetime of 2.2 microseconds corresponds to a travel distance of roughly 660 meters if the particle were moving at the speed of light. Even allowing for velocities slightly below light speed, classical reasoning predicts that most muons produced high in the atmosphere should decay long before reaching Earth's surface. Atmospheric production heights commonly exceed 10 kilometers, an order of magnitude larger than the classical decay distance. Despite this expectation, detectors at sea level register a substantial flux of muons. The observed intensity is far too large to be reconciled with classical decay predictions. This discrepancy demands an explanation rooted in relativistic physics. The relativistic resolution follows directly from time dilation. In the laboratory frame, the muon is moving at high velocity. Its internal decay process evolves according to its proper time, while observers on Earth measure time using laboratory clocks. The relationship between proper time and laboratory time is governed by the Lorentz factor associated with the muon's velocity. As a result, the muon's decay appears slowed in the laboratory frame, extending its observed lifetime. Quantitatively, the mean lifetime measured in the laboratory frame is the rest frame lifetime multiplied by the Lorentz factor. For a muon travelling at 0.998 times the speed of light, the Lorentz factor is approximately 15. In such a case, the laboratory frame lifetime extends to roughly 33 microseconds. At this extended lifetime, the muon can travel several kilometers before decaying, making detection at Earth's surface entirely plausible. Early atmospheric muon experiments focused on measuring muon flux as a function of altitude. Detectors were placed on mountaintops, aboard balloons, and at sea level. By comparing the number of muons detected at different heights, researchers inferred how many muons survived transit through the atmosphere. These measurements could then be compared with theoretical predictions based on relativistic time dilation. One common experimental approach involved counting muons at two altitudes separated by several kilometers. The muon flux decreases with decreasing altitude due to decay and energy loss in the atmosphere. By modeling energy loss through ionization and accounting for the muon velocity distribution, researchers could predict the expected flux at lower altitudes under relativistic and non-relativistic assumptions. The non-relativistic model consistently underpredicted the observed muon flux at low altitude by large factors. When relativistic time dilation was included, the predicted flux aligned closely with experimental measurements. The agreement extended beyond qualitative trends and held quantitatively across a wide range of energies and altitudes. A complementary perspective arises by analysing the experiment from the muon's rest frame. In that frame, the muon's lifetime remains fixed at 2.2 microseconds. The explanation for its survival over long distances then shifts to length contraction. From the muon's perspective, the thickness of Earth's atmosphere is reduced by the same Lorentz factor that dilates time in the laboratory frame. The contracted atmosphere allows the muon to traverse the distance before decaying. This dual description illustrates the internal consistency of special relativity. Both frames yield the same physical outcome using different but equivalent interpretations. In the laboratory frame, time dilation extends the muon's lifetime. In the muon's frame, length contraction reduces the travel distance. Proper time remains invariant in both descriptions. Experimental verification does not rely on frame-dependent narratives. The measurable quantity is the muon count at various altitudes and energies. These counts depend on the decay law expressed in laboratory time and on the muon velocity distribution. Relativistic predictions match observations without adjustable parameters beyond those independently measured. More refined experiments went beyond flux measurements and directly measured muon lifetimes at relativistic speeds. In these experiments, muons were slowed and stopped in dense materials, where their decay products could be detected. By measuring the decay time distribution of muons arriving with different energies, researchers observed the expected increase in mean lifetime with increasing velocity prior to stopping. In atmospheric contexts, energy loss plays a significant role. As muons propagate through air, they lose energy primarily through ionization. This energy loss reduces their velocity over time, changing the Lorentz factor continuously along the trajectory. Accurate modelling requires integrating the decay probability over the muon's path while accounting for the changing velocity. These effects are well understood and quantified. Theoretical models incorporating relativistic decay rates and energy loss reproduce the observed altitude dependence of muon flux with high accuracy. Deviations from predictions fall within experimental uncertainties related to detector efficiency, atmospheric density variations, and cosmic ray intensity fluctuations. The robustness of the muon lifetime experiments lies in their reliance on a fundamental particle process governed by the weak interaction. The muon decay rate is intrinsic and well characterized. Environmental factors such as temperature and pressure influence muon production and propagation only indirectly through atmospheric density, not through the decay mechanism itself. This separation strengthens the interpretation of the results. Muon experiments also demonstrate the universality of time dilation across physical systems. The decay of a muon involves quantum field processes fundamentally different from the oscillations of an atomic clock or a mechanical resonator. The fact that both exhibit the same relativistic time dilation confirms that the effect is not mechanism dependent. Quantitative agreement with special relativity has improved steadily as experimental techniques advanced. Modern detectors with large surface areas and precise timing electronics allow detailed measurements of muon energy spectra and angular distributions. These data further constrain models and continue to validate relativistic predictions at high precision. The atmospheric muon experiments occupy a unique position in the experimental history of relativity. They provided clear evidence of time dilation without requiring human-engineered high-speed clocks. Nature supplied both the relativistic particles and the extreme velocities needed to test the theory. From an operational standpoint, these experiments align directly with the definition of time in terms of clocks. The muon itself functions as a clock, with its decay serving as a time marker. The extended survival of moving muons represents a direct measurement of dilated proper time relative to laboratory time. The agreement between measured muon fluxes and relativistic predictions does not depend on interpretive assumptions about simultaneity or synchronization. It follows from counting particles and measuring decay rates. This simplicity gives the result exceptional evidential weight. Muon lifetime experiments in the atmosphere thus provide a clean and quantitative confirmation of relativistic time dilation. They link microscopic particle physics with macroscopic measurements spanning kilometers of atmosphere. The consistency between theory and observation across these scales establishes time dilation as an experimentally grounded property of nature rather than a theoretical abstraction. Particle accelerators provide controlled, repeatable environments in which relativistic time dilation can be tested with exceptional precision. Unlike atmospheric muon experiments, where particle energies and trajectories are determined by natural processes, accelerators allow physicists to select particle species, energies, velocities, and storage times deliberately. This control turns accelerators into laboratories for studying how unstable particles experience time when moving at relativistic speeds. The fundamental principle underlying accelerator-based tests of time dilation is straightforward. An unstable particle has a well-defined mean lifetime in its rest frame, determined by the interaction responsible for its decay. When that particle is accelerated to a high velocity and observed in the laboratory frame, its decay rate must reflect the relationship between proper time and laboratory time predicted by special relativity. The comparison between rest frame lifetimes and laboratory frame decay times provides a direct quantitative test of relativistic time dilation. Early accelerator experiments focused on particles such as muons, pions, and kaons. These particles are well suited for lifetime measurements because their decay channels are well understood and their rest frame lifetimes fall within a convenient range for laboratory observation. Muons, in particular, played a central role because their lifetime is long enough to allow storage and repeated observation, yet short enough to permit precise statistical analysis over manageable timescales. In circular accelerators, particles are guided along closed paths by magnetic fields. Storage rings and synchrotrons use carefully shaped magnetic fields to bend charged particles into circular orbits, while electric fields provide acceleration and energy control. Once injected into a storage ring at relativistic speed, particles can circulate for extended periods, completing millions of revolutions before decaying or being lost due to interactions with residual gas or beam instabilities. From an experimental perspective, a storage ring offers a key advantage. The particle's velocity remains approximately constant over long durations. This stability simplifies the relationship between proper time and laboratory time. The Lorentz factor associated with the particle's velocity can be determined independently from its momentum and mass, allowing a direct prediction of the expected time dilation. In these experiments, the decay of particles is detected by surrounding detectors that record the appearance of decay products. For muons, decay electrons or positrons are detected, while for hadrons, such as kaons, characteristic decay modes involving pions or leptons are monitored. The decay time distribution measured in the laboratory frame is then compared with the expected exponential decay law modified by relativistic time dilation. The essential observable is the mean lifetime measured in the laboratory frame. According to special relativity, this lifetime equals the rest frame lifetime multiplied by the Lorentz gamma factor associated with the particle's velocity. By varying the particle energy, experiments can probe different gamma factors and test whether the measured lifetimes scale accordingly. One of the earliest and most influential accelerator-based tests involved muons stored in circular rings. Muons were produced by pion decay, captured and injected into storage rings where their motion was maintained by magnetic fields. As the muons circulated, their decay electrons were detected, allowing the decay rate to be measured as a function of laboratory time. these experiments confirmed that the observed muon lifetime increased precisely in proportion to the Lorentz gamma factor. Measurements were consistent across a wide range of velocities, extending well into the relativistic regime. The agreement between theory and experiment was quantitative, not merely qualitative, with discrepancies falling within experimental uncertainties. An important feature of circular motion experiments is the presence of centripetal acceleration. Particles in a storage ring experience continuous acceleration due to their curved trajectory, even though their speed remains constant. This raised early questions about whether acceleration might influence decay rates independently of velocity. Experimental results showed that the decay rate depends on velocity through the Lorentz factor and remains unaffected by the presence of centripetal acceleration itself. This finding reinforces a key principle of special relativity. Time dilation depends on instantaneous velocity, not on acceleration per se. Proper time accumulates along a world line according to the space-time metric, and acceleration influences the shape of that world line without introducing additional time dilation effects beyond those associated with velocity. Synchrotrons extended these studies by allowing particles to reach even higher energies. In a synchrotron, the magnetic field strength increases as the particle energy increases, maintaining a fixed orbital radius while accelerating the particles to ever higher speeds. This design enables systematic exploration of time dilation over a broad range of Lorentz factors. Experiments with unstable hadrons, such as charged kaons, provided further confirmation. Kaons have shorter rest frame lifetimes than muons, but their decay signatures are distinctive and detectable. By accelerating kaons to high energies and measuring their decay lengths and times, researchers observed lifetime extensions consistent with relativistic predictions. In many cases, decay length measurements offered an alternative approach. Instead of measuring decay times directly, experiments measured the distance travelled by particles before decay. The decay length in the laboratory frame depends on the particle's velocity and dilated lifetime. By combining measured decay lengths with independently determined velocities, experiments extracted laboratory lifetimes and compared them with rest frame values. This method proved particularly effective for very short-lived particles. When lifetimes are too short for direct time measurement, decay lengths provide a spatial proxy for temporal information. Relativity links space and time in such a way that spatial measurements can reveal temporal dilation. Precision improved as accelerator technology advanced, beam energies became more stable, detectors more sensitive, and data acquisition systems more sophisticated. Statistical uncertainties decreased as larger data samples became available. Systematic uncertainties were reduced through careful calibration and cross-checks. A notable aspect of these experiments is the precision with which Lorentz gamma factors could be determined. Particle momentum and energy measurements in accelerators are highly accurate, relying on magnetic field calibration and beam diagnostics. This precision allows detailed comparisons between measured lifetimes and relativistic predictions without adjustable parameters. Modern accelerator experiments continue this tradition at facilities such as CERN. High-energy storage rings and collider complexes produce vast numbers of unstable particles, enabling lifetime measurements with unprecedented accuracy. Although the primary goals of these facilities often involve probing fundamental interactions, the data they produce also provide ongoing confirmation of relativistic time dilation. An important conceptual point emerges from accelerator-based tests. The particles under study are quantum systems governed by quantum field theory, while time dilation arises from space-time geometry described by special relativity. The agreement between measured decay rates and relativistic predictions demonstrates the consistency between quantum processes and relativistic kinematics. The decay probability evolves according to proper time, linking quantum dynamics directly to relativistic time. These experiments also underscore the universality of time dilation. muons, pions, kaons, and other unstable particles exhibit the same scaling of lifetime with Lorentz factor, despite differences in mass, internal structure, and decay mechanism. This universality confirms that time dilation is not sensitive to the details of the decay process. The role of accelerators as time dilation laboratories extends beyond particle lifetimes. In some experiments, oscillatory processes such as spin precession are used as clocks. The rate of spin precession depends on proper time, and measurements of precession frequencies at relativistic speeds provide additional confirmation of time dilation effects. In all cases, the operational definition of time remains central. The particle's decay or oscillation serves as a clock, and the comparison between proper time and laboratory time reveals the effect of motion. The laboratory frame provides the coordinate time, while the particle's internal evolution provides the proper time. Accelerator-based experiments also help clarify the distinction between kinematic and gravitational time dilation. In these laboratory settings, gravitational potential differences are negligible compared to velocity effects. The observed lifetime extensions therefore isolate the kinematic component predicted by special relativity. The cumulative evidence from storage rings and synchrotrons establishes time dilation as a quantitatively verified phenomenon across an enormous range of energies. From modest relativistic speeds to Lorentz factors of thousands, the scaling of lifetime with velocity follows the Lorentz transformation precisely. Particle accelerators thus serve as precise and versatile laboratories for testing the foundations of relativistic time. By combining controlled conditions, well-understood particle properties, and high-precision measurements, they transform an abstract prediction into a repeatedly verified experimental fact. The first transported clock experiments marked the transition from indirect tests of relativistic time dilation, such as particle lifetimes, to direct comparisons between macroscopic clocks following different trajectories. These experiments took place before the advent of ultra-stable optical clocks and even before the widespread availability of space-based platforms. They relied on quartz oscillators and early atomic clocks physically moved by aircraft or ground vehicles, then compared with reference clocks that remained stationary. Although limited in precision by technology, these experiments established the operational feasibility of measuring time dilation using transported clocks and clarified the experimental challenges involved. The central idea behind transported clock experiments is operationally simple. Two clocks are synchronized while co-located. One clock remains at a reference location, while the other is transported along a trajectory involving motion relative to the reference frame. After transport, the clocks are reunited and compared directly. Any difference in accumulated time reflects the integrated proper time along each clock's path. This procedure avoids many conceptual complications associated with distant synchronization. Because the clocks are compared side by side at the end of the experiment, signal propagation delays and simultaneity conventions play no role in the final comparison. The experiment reduces to a comparison of accumulated clock readings. Early attempts to implement this idea faced substantial technical obstacles. The first challenge involved clock stability. Quartz clocks, which were among the most precise portable timekeeping devices available in the mid-20th century, exhibited frequency drifts due to temperature changes, mechanical stress, and aging of the crystal. These effects could easily overwhelm the small, relativistic time differences expected from terrestrial transport. The expected magnitude of kinematic time dilation in early experiments was extremely small. For an aircraft travelling at several hundred kilometers per hour, the relativistic correction over a flight lasting a few hours amounts to tens of nanoseconds or less. Detecting such a small effect required clocks with stability and reproducibility well beyond everyday standards. Despite these limitations, early experiments demonstrated that meaningful comparisons were possible. One approach involved transporting clocks over long distances by ground vehicles or aircraft and comparing them with stationary clocks using careful calibration procedures. By repeating the transport multiple times and averaging results, researchers sought to distinguish systematic relativistic effects from random clock noise. Quartz clocks played a key role in these early efforts. Their operation is based on the mechanical resonance of a piezoelectric crystal, typically vibrating at a frequency of tens of kilohertz or higher. While less stable than atomic clocks, quartz oscillators offered portability and robustness. They could survive transport without catastrophic damage, making them suitable for experimental trials. However, quartz clocks are sensitive to vibration and acceleration. Transport by aircraft or vehicle subjects the clock to continuous mechanical disturbances. Vibrations can alter the effective resonance frequency of the crystal, introducing transient frequency shifts that integrate into timing errors. Separating these effects from relativistic time dilation required careful experimental design. Researchers addressed vibration sensitivity by mounting clocks in shock-absorbing enclosures and characterizing their response to known acceleration profiles. Ground tests were performed to measure how clock rates changed under controlled vibration and acceleration conditions. These calibrations informed corrections applied to transported clock data. Temperature sensitivity presented another major challenge. Quartz oscillators exhibit frequency drift as a function of temperature. Aircraft cabins and cargo holds experienced temperature variations during flight, particularly in early aircraft, without precise environmental control. To mitigate this effect, clocks were often housed in temperature-regulated containers. Even so, residual temperature fluctuations contributed to timing uncertainty. Synchronization error imposed an additional limitation. Initial synchronization of clocks had to be performed with sufficient precision to ensure that post-transport differences could be attributed meaningfully to relativistic effects. Early synchronization methods relied on direct electrical connections or radio signals, both of which introduced uncertainty at the nanosecond level or higher. As atomic clocks became portable, they began to replace quartz clocks in transported clock experiments. Cesium beam clocks, based on the hyperfine transition of cesium-133, offered orders of magnitude improvement in frequency stability. These clocks defined time through an atomic transition rather than a mechanical resonance, making them less sensitive to vibration and temperature. The introduction of portable atomic clocks marked a turning point. Although still bulky and delicate by modern standards, early cesium clocks could be transported by aircraft with careful handling. Their improved stability made relativistic effects measurable over realistic transport durations. In early atomic clock transport experiments, researchers focused on establishing baseline behavior. Clocks were transported over short distances and compared repeatedly to characterize systematic errors. Only after demonstrating reproducibility did experiments attempt longer journeys or higher velocities. One important insight from these experiments involved the role of acceleration. Transported clocks experience acceleration during takeoff, landing, and turns. Classical intuition suggested that acceleration might influence clock rates directly. Experimental evidence showed that any such effects were negligible compared to velocity-dependent time dilation, consistent with relativistic predictions that proper time depends on velocity rather than acceleration itself. Ground transport experiments offered complementary information. Vehicles traveling at lower speeds produced smaller relativistic effects, but allowed more controlled environments. Ground experiments helped isolate non-relativistic influences, such as vibration and temperature drift, providing a reference against which aircraft experiments could be compared. Data analysis in early transported clock experiments required careful statistical treatment. Individual clock comparisons often exhibited noise larger than the expected relativistic signal. By repeating experiments and averaging results, researchers reduced random errors and identified consistent trends correlated with velocity and travel duration. One methodological advance involved transporting clocks in opposite directions along similar routes. By comparing eastward and westward transport, researchers could isolate velocity-dependent effects relative to Earth's rotation. Although the full implications of Earth's rotation were explored more thoroughly in later experiments, early transported clock studies already recognized the importance of directionality. These early experiments clarified the separation between kinematic and gravitational effects. For terrestrial transport over modest altitude changes, gravitational time dilation was small but not negligible. Differences in altitude between the reference clock and the transported clock introduced additional proper time differences. Accounting for these effects required incorporating gravitational potential corrections based on general relativity. At this stage, gravitational corrections were often treated approximately. The focus remained on demonstrating that motion-induced effects were observable and consistent with relativistic expectations. Later experiments refined these corrections as clock precision improved. Despite their limitations, early transported clock experiments achieved several important goals. They demonstrated that macroscopic clocks could survive transport and retain sufficient stability for meaningful comparison. They established experimental protocols for synchronization, transport, and reunion. They identified dominant sources of error and methods for mitigating them. Perhaps most importantly, these experiments showed that time dilation could be studied directly using human-engineered clocks rather than inferred from particle behavior. This shift had conceptual significance. It reinforced the operational definition of time as something measured by clocks, regardless of scale or mechanism. The limitations encountered in early experiments also shaped future developments. The need for greater stability motivated improvements in atomic clock design. The sensitivity to vibration and temperature led to better environmental control and clock packaging. Synchronization challenges spurred advances in time transfer techniques. These early transported clock experiments laid the groundwork for more definitive tests. As clock technology advanced, the same basic experimental concept would be applied with far greater precision, eventually enabling clear separation of kinematic and gravitational contributions and quantitative agreement with relativistic predictions. In retrospect, the first transported clock experiments occupy a transitional position in the experimental history of relativity. They bridged the gap between indirect tests and high-precision clock comparisons. Their results, while limited in accuracy, consistently aligned with relativistic expectations and strengthened confidence in the theory. By transforming time dilation from a phenomenon inferred through particles and thought experiments into one measured by transported clocks, these experiments advanced the empirical foundation of relativistic time. They demonstrated that even with imperfect technology, the effects predicted by relativity were accessible to direct measurement, provided experimental care and operational clarity were maintained. The Hafele-Keating experiment represents a decisive moment in the experimental study of relativistic time dilation using macroscopic clocks. It was the first experiment to combine high-precision atomic clocks, long-distance transport, and a full accounting of both kinematic and gravitational effects within a single closed experimental design. By flying atomic clocks around the Earth and comparing them directly with reference clocks that remained stationary, the experiment translated relativistic predictions into a concrete, testable procedure. The experiment was conceived and carried out in the early 1970s by Joseph Hafele and Richard Keating. Its significance lies not in introducing new relativistic theory, but in subjecting well-established theoretical predictions to a demanding real-world test that incorporated Earth's rotation, gravity, and realistic clock behavior. The central experimental idea followed the transported clock logic developed earlier. Several cesium beam atomic clocks were synchronized with reference clocks at a fixed laboratory. These clocks were then flown around the Earth on commercial aircraft, first eastward and then westward, before being returned and directly compared with the original reference clocks. The accumulated differences in elapsed time were interpreted in terms of relativistic effects. Cesium clocks were chosen because they represented the most stable portable time standards available at the time. Each clock defined time using the hyperfine transition frequency of cesium-133, a process known for its reproducibility and insensitivity to many environmental disturbances. Even so, the clocks were far less stable than modern atomic or optical clocks, which made careful error analysis essential. The experiment involved 4 cesium clocks, transported together to reduce relative drift uncertainties. Prior to the flights, all clocks were synchronized and compared extensively to establish baseline behavior and quantify mutual drift rates. This calibration phase was critical as the relativistic effects to be measured were comparable in magnitude to the intrinsic drift of the clocks over several days. 2 complete circumnavigations of the Earth were performed. In the first, the clocks were flown eastward, in the same direction as Earth's rotation. In the second, they were flown westward, opposite to Earth's rotation. Each trip lasted several days and involved multiple flight segments, with clocks remaining aboard the aircraft continuously. The relativistic predictions required careful separation of 2 distinct effects: kinematic time dilation and gravitational time dilation. The kinematic contribution arises from relative velocity. A clock moving with respect to an Earth-centered inertial frame accumulates less proper time than a clock at rest in that frame. Because Earth itself rotates, a clock on the ground already has a velocity relative to an inertial frame centered at Earth's center. An aircraft flying eastward increases its speed relative to this inertial frame, while a westward flying aircraft reduces it. As a result, kinematic time dilation predicts that eastward flying clocks should lose time relative to ground clocks, while westward flying clocks should gain time. The magnitude of this effect depends on the aircraft's speed, latitude, and duration of flight. The gravitational contribution arises from differences in gravitational potential. According to general relativity, a clock at higher altitude runs faster than a clock at lower altitude. Aircraft cruise at altitudes of roughly 10 kilometers, placing the airborne clocks at a slightly higher gravitational potential than clocks on the ground. This effect causes airborne clocks to gain time relative to ground clocks, regardless of direction of flight. The total predicted time difference for each flight is the sum of these 2 contributions. For eastward flights, the kinematic loss dominates over the gravitational gain, leading to a net loss of time. For westward flights, the kinematic gain and gravitational gain add together, leading to a net gain of time. Before the experiment, Hayfile and Keating calculated the expected time differences using established relativistic formulas. These calculations required integrating the proper time along the actual flight paths, accounting for variations in speed, altitude, and latitude. Simplifying assumptions were made where appropriate, but the calculations were grounded in measurable quantities. The predicted results were on the order of tens to hundreds of nanoseconds. Specifically, eastward flights were expected to result in a net time loss of roughly 40 nanoseconds, while westward flights were expected to produce a net gain of roughly 200 nanoseconds. These values were well within the resolution limits of cesium clocks, but small enough that systematic errors could not be ignored. After completing the flights, the transported clocks were compared directly with the reference clocks. The observed time differences were consistent with relativistic predictions within experimental uncertainty. Eastward flown clocks lost time and westward flown clocks gained time, with magnitudes close to those predicted. The experimental results were not exact matches to theoretical values, and this discrepancy sparked discussion and criticism. The reported uncertainties were substantial, reflecting both clock drift and environmental influences. However, the sign and approximate magnitude of the effects aligned with relativistic predictions in both cases, which was the primary experimental objective. Error analysis played a central role in the interpretation of the experiment. Several sources of uncertainty were identified and quantified. Clock drift was the largest contributor. Cesium clocks of that era exhibited frequency instabilities that accumulated over days. Haffel and Keating estimated drift rates based on pre-flight and post-flight comparisons and incorporated these into the uncertainty budget. Environmental effects such as temperature variations, pressure changes, and vibration also influenced clock behavior. Aircraft cabins did not provide the controlled environments available in laboratories. The clocks were insulated and monitored, but residual environmental sensitivity remained. Velocity variations introduced additional uncertainty. Aircraft speed varied between flight segments and was influenced by winds and operational constraints. Accurate modelling required using actual flight data rather than nominal cruise speeds. Altitude variations affected gravitational time dilation. Aircraft do not maintain perfectly constant altitude, and variations of even a few hundred meters influence the gravitational contribution at the nanosecond level. These variations were estimated from flight logs. Relativistic corrections related to Earth's rotation and non-inertial reference frames added further complexity. The Earth-fixed frame is not inertial, and the calculation of kinematic effects required careful definition of the reference frame relative to which velocities were measured. Despite these challenges, the overall agreement between theory and experiment was compelling. The experiment demonstrated that relativistic time dilation was not confined to idealized laboratory conditions or microscopic particles. It applied to real clocks, moving at everyday speeds around a rotating, gravitating planet. One of the most important outcomes of the Haffel-Keating experiment was conceptual clarity. It showed explicitly how kinematic and gravitational effects combine in practical situations. The experiment made clear that relativistic time dilation is not a single effect, but the result of multiple contributions that must be summed along a clock's trajectory. The experiment also highlighted the operational meaning of time in relativity. Time differences were not inferred from signal delays or distant synchronization. They were measured by transporting clocks, reuniting them, and comparing accumulated readings. This directness gave the result a particular experimental strength. Subsequent experiments with improved clocks and more controlled conditions refined these measurements dramatically. Modern aircraft experiments using optical clocks achieve precision many orders of magnitude better. Satellite-based systems incorporate relativistic corrections continuously. These later developments do not replace the Haffel-Keating experiment. They build upon its conceptual and methodological foundation. The Haffel-Keating experiment remains historically significant because it confronted relativity with the complexity of the real world. It accounted for Earth's rotation, gravity, imperfect clocks, and noisy environments. The fact that relativistic predictions survived this confrontation reinforced confidence in the theory's applicability beyond idealized settings. In the broader context of experimental relativity, the experiment occupies a unique position. It stands between early, low-precision transported clock tests and modern, ultra-precise clock networks. It demonstrated that even with the technological limitations of the time, relativistic time dilation was measurable, directional, and quantitatively meaningful. By showing that atomic clocks flown around the Earth accumulate time in precise accordance with relativistic predictions, the Haffel-Keating experiment transformed time dilation from a laboratory curiosity into a global, operationally verified phenomenon. Modern aircraft experiments using optical atomic clocks represent a major advance in the direct measurement of relativistic time dilation. These experiments build on the conceptual framework established by earlier transported clock studies, while exploiting dramatic improvements in clock stability, accuracy, and time transfer techniques. As a result, relativistic effects that once required days of flight and large statistical averaging can now be detected over flight durations of hours or even minutes, with clear quantitative agreement between measurement and theory. Optical clocks differ fundamentally from earlier microwave atomic clocks in the frequency of the reference transition used to define time. While cesium clocks rely on microwave transitions with frequencies on the order of gigahertz, optical clocks use electronic transitions in atoms or ions with frequencies hundreds of thousands of times higher. This increase in frequency translates directly into improved time resolution. Each tick of the clock corresponds to a much shorter interval, allowing smaller relativistic effects to accumulate into measurable phase differences. The stability of an atomic clock is commonly characterized by its fractional frequency uncertainty. Early cesium clocks achieved uncertainties at the level of 1 part in 10 to the power of 13 to 10 to the power of 14. Modern optical clocks routinely reach uncertainties below 1 part in 10 to the power of 18. At this level, relativistic time dilation effects associated with everyday velocities and altitude changes become experimentally accessible. The operational principle of modern aircraft clock experiments remains the same as in earlier transported clock studies. 2 or more clocks are synchronized at a common location. One clock remains stationary, while another is transported aboard an aircraft along a well-defined trajectory. After transport, the clocks are compared, and the accumulated difference in elapsed proper time is measured. The novelty lies in the sensitivity of the clocks and the precision with which the trajectory can be characterized. Optical clocks used in these experiments are typically based on atoms such as strontium, ytterbium, or aluminum ions. Neutral atom optical lattice clocks trap thousands of atoms in a standing wave of laser light, while ion clocks confine single ions in electromagnetic traps. In both cases, lasers probe ultra-narrow electronic transitions whose frequencies are extraordinarily stable. Achieving portability with such clocks required significant technological development. Early optical clocks were confined to laboratory environments with extensive vibration isolation, temperature control, and complex optical setups. Advances in laser stabilization, compact vacuum systems, and robust frequency comb technology made it possible to package optical clocks into transportable systems suitable for aircraft deployment. One of the key enabling technologies is the optical frequency comb. Frequency combs provide a coherent link between optical frequencies and microwave frequencies, allowing precise comparison between optical clocks and other time standards. They also facilitate high-precision time transfer between clocks before and after transport. In modern aircraft experiments, synchronization between clocks is performed with extreme care. Prior to flight, clocks are compared over extended periods to characterize relative drift and establish a stable baseline. During the flight, environmental conditions are monitored continuously, and post-flight comparisons are conducted immediately to minimize unmodeled drift. Short-duration flights represent a defining feature of these experiments. With optical clocks, measurable relativistic offsets can accumulate over flight times of just a few hours. In some cases, altitude changes of a few kilometers and velocities typical of commercial aircraft are sufficient to produce time differences well above the noise floor of the clocks. The relativistic contributions to the measured time difference are computed by integrating the proper time along the clock's world line. This calculation includes both kinematic and gravitational components. The kinematic contribution depends on the aircraft's velocity relative to an Earth-centered inertial frame, while the gravitational contribution depends on the clock's altitude and the local gravitational potential. Accurate evaluation of these integrals requires detailed knowledge of the aircraft's trajectory. Modern experiments use high-resolution GPS data, inertial navigation systems, and flight telemetry to reconstruct velocity and altitude as functions of time. This information allows precise calculation of the expected relativistic time offset. In contrast to earlier experiments, uncertainties associated with synchronization and clock drift are now often smaller than uncertainties associated with trajectory modeling. The limiting factor is no longer clock performance, but the accuracy with which velocity, altitude, and gravitational potential are known. Gravitational time dilation plays a particularly prominent role in aircraft experiments. At cruising altitude, an aircraft is typically several kilometers above Earth's surface. At optical clock precision, a height difference of even 1 meter produces a measurable frequency shift. Aircraft altitude variations during flight therefore contribute significantly to the accumulated proper time difference. Kinematic time dilation remains important, but is often comparable in magnitude to the gravitational contribution. Depending on flight direction, speed, and latitude, the kinematic effect can either partially cancel or reinforce the gravitational effect. Modern experiments exploit this sensitivity to test theoretical predictions under different conditions. A notable feature of optical clock aircraft experiments is their ability to compare measured time offsets directly with predicted proper time integrals without adjustable parameters. The rest frame frequency of the clock transition is known independently. The trajectory is measured independently. Relativity provides the mapping from trajectory to accumulated proper time. Agreement between prediction and measurement thus constitutes a stringent test of the theory. Several landmark experiments have demonstrated this capability. Research groups associated with institutions such as National Institute of Standards and Technology have flown optical clocks aboard aircraft and compared them with stationary reference clocks. These experiments achieved agreement with relativistic predictions at the level of a few parts in 10 to the 17th power, or better. One important outcome of these studies is the confirmation that relativistic time dilation applies uniformly across vastly different clock technologies. Optical clocks, based on different atomic species and trapping methods, all exhibit the same relativistic behavior when subjected to the same motion and gravitational potential. This universality reinforces the interpretation of time dilation as a property of space-time rather than of specific physical systems. Modern aircraft experiments also provide a bridge between laboratory tests and space-based applications. The techniques developed for portable optical clocks, precise time transfer, and trajectory reconstruction are directly applicable to satellite missions and deep space navigation. Aircraft experiments serve as test beds for technologies that will operate in more extreme environments. The comparison between measured and predicted proper time often reveals subtle effects that were previously inaccessible. For example, variations in Earth's gravitational potential due to latitude, Earth's rotation, and local mass distribution can produce detectable signatures in optical clock data. While these effects are small, they must be included in high-precision modelling. Environmental sensitivity remains an experimental concern, though its role has shifted. Optical clocks are less sensitive to vibration than quartz clocks, but they remain sensitive to temperature, magnetic fields, and laser noise. Modern experiments mitigate these influences through active stabilization, shielding, and real-time monitoring. Acceleration effects during takeoff, landing, and turbulence are carefully analysed. Experimental evidence continues to support the relativistic prediction that acceleration influences clock readings only indirectly through its effect on velocity and gravitational potential, not through additional time dilation terms. The statistical treatment of data in modern experiments reflects the high precision achieved. Rather than averaging over large noise, researchers focus on identifying and correcting systematic effects. Uncertainty budgets are constructed that include contributions from clock stability, trajectory reconstruction, gravitational modelling, and time transfer accuracy. One conceptual advance enabled by optical clocks is the ability to resolve relativistic time dilation locally. Experiments have demonstrated measurable frequency shifts when clocks are moved vertically by small distances within a laboratory. Aircraft experiments extend this capability to dynamic trajectories, integrating local effects over extended paths. The agreement between experiment and theory in these studies is not limited to qualitative trends. Measured time offsets match predicted values within stated uncertainties, often at levels that challenge the limits of current modelling. Deviations provide opportunities to refine experimental techniques rather than indications of new physics. Modern aircraft experiments also underscore the operational meaning of proper time. The clock carried aboard the aircraft accumulates time according to its world line. The stationary clock accumulates time according to a different world line. The difference between their readings is a direct measurement of the difference in proper time between those paths. This perspective aligns seamlessly with the relativistic framework developed for particles, satellites, and laboratory clocks. The same mathematical formalism applies across all scales. Optical clock experiments simply push the sensitivity of measurement to new extremes. In the broader context of experimental relativity, modern aircraft optical clock experiments represent a culmination of decades of technological progress. They transform relativistic time dilation from a correction applied to navigation systems into a routinely measured laboratory quantity. By demonstrating that short-duration flights produce measurable, predictable relativistic time offsets, these experiments confirm the internal consistency of relativity with unprecedented precision. They also establish a foundation for future studies that will extend precision timekeeping beyond Earth, where relativistic effects play an even more central role. The use of optical clocks aboard aircraft thus marks a new phase in the experimental study of time. Motion, gravity, and timekeeping converge in a regime where relativistic effects are not only detectable but precisely quantifiable, reinforcing time dilation as one of the most rigorously tested predictions in physics. Time dilation in global navigation satellite systems provides one of the most practical, continuously operating demonstrations of relativistic physics. Unlike laboratory experiments that test relativity over limited durations, satellite navigation systems apply relativistic corrections at all times as an essential part of their operation. Without these corrections, the systems would fail rapidly and predictably. The success of satellite navigation therefore rests directly on the correct application of both kinematic and gravitational time dilation. Global navigation satellite systems rely on precise time measurement. Position is determined by measuring the travel time of radio signals from satellites to receivers on Earth. Each satellite carries multiple atomic clocks that broadcast time-stamped signals. A receiver compares the time of reception with the transmitted timestamps to infer distances. An error of 1 nanosecond corresponds to a position error of roughly 30 centimeters. This sensitivity places stringent requirements on clock accuracy and stability. Satellite clocks operate in an environment very different from clocks on Earth's surface. They move at high orbital velocities and reside at higher gravitational potential. Both factors alter the rate at which the clocks tick relative to clocks on the ground. These rate differences are not incidental corrections. They dominate the long-term behavior of the system. The kinematic contribution arises from orbital motion. Navigation satellites orbit Earth at speeds of several kilometers per second. Relative to an Earth-centered inertial frame, this velocity produces special relativistic time dilation. A moving clock ticks more slowly than a stationary one, as measured in that inertial frame. For navigation satellites, the kinematic effect causes onboard clocks to lose time relative to clocks on Earth's surface. The gravitational contribution arises from general relativity. Clocks located higher in a gravitational potential tick faster than clocks deeper in the gravitational field. Navigation satellites orbit at altitudes of roughly 20,000 kilometers above Earth's surface. At this altitude, the gravitational potential is significantly higher than on the ground. This effect causes satellite clocks to gain time relative to Earth-based clocks. The two contributions act in opposite directions. The kinematic effect slows satellite clocks, while the gravitational effect speeds them up. The net effect depends on the specific orbital parameters of the system. For satellites used in systems such as Global Positioning System, the gravitational contribution dominates. The net result is that satellite clocks tick faster than ground clocks by approximately 38 microseconds per day. This offset is large compared to the tolerances required for navigation accuracy. If left uncorrected, this timing error would accumulate rapidly. A drift of 38 microseconds per day corresponds to a ranging error of roughly 11 kilometers per day. Within minutes, position errors would exceed acceptable limits. Within a day, the system would be unusable. The necessity of relativistic correction in satellite navigation is therefore not subtle or marginal. It is decisive. The system architecture incorporates relativistic physics at the most fundamental level. The solution adopted in navigation systems involves a combination of pre-launch clock offsetting and continuous correction. Satellite clocks are designed to tick at a slightly slower rate on the ground, so that once in orbit, their relativistic rate matches the coordinate time used by the system. This adjustment accounts for the average gravitational and kinematic effects. In addition to this static offset, continuous corrections are required. Satellite orbits are not perfectly circular, and velocities vary slightly over each orbit. These variations produce periodic relativistic effects that must be corrected dynamically. The system broadcasts parameters that allow receivers to compute these corrections in real time. The timescale used by navigation systems is a coordinate time defined in an Earth-centered reference frame. Ground-based control stations maintain this timescale by comparing ensembles of atomic clocks and steering the system accordingly. Satellite clocks are synchronized to this coordinate time through uplink commands and onboard adjustments. From an operational perspective, the satellite clock measures its own proper time along its world line. The navigation system requires a mapping between this proper time and the coordinate time used to define positions. Relativity provides that mapping. An additional relativistic effect arises from the eccentricity of satellite orbits. As a satellite moves closer to Earth at perigee and farther away at apogee, both its velocity and gravitational potential change. These variations cause periodic modulations in the clock rate. The resulting time offset depends on orbital phase and must be accounted for to maintain accuracy. Another effect involves Earth's rotation. Signals transmitted from satellites propagate through a rotating reference frame. This leads to a relativistic correction associated with non-inertial motion, often treated separately from time dilation but derived from the same space-time framework. Accurate positioning requires incorporating this effect into signal timing. The inclusion of relativistic corrections in navigation systems is not an afterthought added to classical physics. It is an integral part of system design. Early system architects recognized that relativistic effects would dominate timing errors and incorporated them from the outset. This recognition was based on quantitative predictions rather than empirical tuning. The magnitude of the expected relativistic offsets could be calculated precisely from orbital parameters and gravitational models. The fact that these predictions matched observed system behavior provided a strong validation of relativistic theory in an applied context. Other global navigation systems follow the same principles. Systems such as Galileo and GLONASS incorporate relativistic corrections tailored to their specific orbital configurations and time scales. Despite differences in implementation, all systems rely on the same underlying physics. The continuous nature of relativistic correction in navigation systems distinguishes them from discrete experiments. Every position fix computed by a receiver implicitly assumes that relativistic time dilation is real and quantitatively accurate. The system's performance over decades serves as an ongoing experiment in relativistic physics. Clock stability remains a critical factor. Modern navigation satellites carry multiple atomic clocks, typically cesium or rubidium standards. These clocks exhibit excellent long-term stability, but still require periodic correction. Relativistic modeling ensures that corrections address genuine physical effects rather than compensating for misinterpreted drift. The operational success of navigation systems also clarifies the separation between kinematic and gravitational time dilation. Both effects are present simultaneously and must be treated distinctly. Attempts to attribute observed offsets to only one contribution fail quantitatively. The correct result emerges only when both are included. From the standpoint of experimental verification, satellite navigation provides an unusually stringent test. The system's accuracy is monitored continuously, and discrepancies are quickly identified. The absence of unexplained timing drift over long periods supports the correctness of relativistic modeling at the required precision. The catastrophic failure that would result from ignoring relativity underscores the physical reality of time dilation. This is not an effect that appears only under extreme conditions or specialized experiments. It manifests in everyday technology used by millions of people. In conceptual terms, navigation systems operationalize the distinction between proper time and coordinate time. Each satellite clock follows its own proper time. The system defines a shared coordinate time, unlocking precise spatial relationships. Relativity provides the transformation between the two. The fact that this transformation works reliably across thousands of satellites, billions of receivers, and decades of operation reinforces the interpretation of time dilation as a fundamental property of space-time rather than a theoretical abstraction. Global navigation satellite systems thus occupy a central position in the experimental landscape of relativity. They demonstrate that relativistic time dilation is not only measurable but indispensable. Without it, modern navigation would not function. By embedding relativistic corrections into everyday infrastructure, these systems provide continuous, large-scale confirmation of the relativistic relationship between motion, gravity, and time. The success of satellite navigation stands as one of the clearest practical validations of relativistic time dilation ever achieved. Laboratory tests of velocity-dependent time dilation conducted entirely on Earth provide a controlled and conceptually clean confirmation of special relativity. These experiments isolate the kinematic component of time dilation by comparing clocks subjected to different tangential velocities while remaining at nearly identical gravitational potential. By doing so, they demonstrate that time dilation arises from motion alone and does not require altitude differences, orbital motion, or large-scale trajectories. The guiding principle of these experiments is operational. Two clocks are placed in the same laboratory environment, synchronized and then subjected to different velocities through rotation. One clock remains near rest with respect to the laboratory, while the other is carried on a rotating platform or centrifuge. After a defined interval, the clocks are compared. Any accumulated difference in elapsed time reflects the dependence of proper time on velocity. Rotation provides a convenient way to achieve sustained high velocities over long durations without transporting clocks over large distances. In a rotating system, tangential velocity increases linearly with radius for a given angular speed. By placing clocks at different radii, experimenters can generate substantial velocity differences while keeping the clocks close together spatially. Early laboratory demonstrations used mechanical or quartz clocks mounted on rotating turntables. These experiments were limited by clock stability and mechanical sensitivity, but they established the feasibility of rotation-based tests. As atomic clocks became available, the precision of such experiments increased dramatically. A typical experimental setup involves a precision clock placed on a rotor with well-characterized angular velocity. The rotor may take the form of a turntable or a centrifuge, capable of maintaining stable rotation for extended periods. A reference clock remains stationary in the laboratory frame. Both clocks are shielded from environmental disturbances and monitored continuously. The relativistic prediction for such an experiment follows directly from special relativity. The proper time accumulated by a clock moving at tangential speed depends on its velocity relative to an inertial frame. For speeds much less than the speed of light, the time dilation effect is small but measurable with sufficiently precise clocks. The accumulated time difference grows with both the square of the velocity and the duration of the experiment. One advantage of laboratory rotation experiments is the ability to reverse configurations. By placing clocks alternately on the rotor and at rest, or by changing rotation direction, experimenters can check for systematic effects unrelated to velocity. True relativistic time dilation depends only on speed, not on direction of motion, providing a clear diagnostic. Gravitational effects are minimized in these setups. The clocks remain at nearly the same height above Earth's surface, so gravitational time dilation contributes negligibly to the observed differences. This allows the experiment to isolate kinematic time dilation with minimal modeling complexity. Centrifugal acceleration is present in rotating systems, and its role requires careful consideration. In special relativity, proper time depends on the instantaneous velocity of a clock, not directly on acceleration. A clock undergoing circular motion experiences continuous acceleration, but maintains constant speed. Experiments confirm that the observed time dilation corresponds to velocity alone, with no additional contribution attributable to acceleration itself. This distinction is experimentally important. If acceleration influenced clock rates independently, rotating experiments would deviate from relativistic predictions. The absence of such deviations supports the relativistic treatment of time as determined by space-time geometry rather than by forces acting on clock mechanisms. Atomic clocks used in these experiments include cesium beam clocks, hydrogen masers, and more recently optical clocks. Each offers different trade-offs between stability, size, and environmental sensitivity. Hydrogen masers, for example, provide excellent short-term stability, making them well suited for experiments lasting hours. Optical clocks provide superior long-term accuracy and allow detection of extremely small relativistic effects. Clock comparison methods are critical. In many experiments, clocks are compared continuously using phase comparison techniques rather than only before and after rotation. Continuous comparison allows time differences to be tracked as a function of rotation speed and duration, improving statistical confidence and enabling real-time monitoring of systematic effects. Time transfer between rotating and stationary clocks requires careful engineering. Electrical connections can introduce noise and phase shifts due to mechanical motion. Optical fiber links and wireless microwave links are often used, with corrections applied for path length changes caused by rotation. One class of experiments places one clock at the center of rotation and another at the rim. The central clock has negligible tangential velocity, while the rim clock reaches the maximum speed. This configuration maximizes velocity difference while minimizing gravitational and environmental differences. The predicted time difference between the two clocks is proportional to the integral of the squared tangential velocity over time. By measuring this difference and comparing it with the calculated value based on rotation speed and radius, experimenters directly test the Lorentz factor dependence. Results from such experiments consistently match relativistic predictions within experimental uncertainty. The agreement holds across different clock technologies and rotation speeds. Deviations are attributable to known systematic effects rather than to unmodeled physics. An important refinement involves varying rotation speed during the experiment. By accelerating and decelerating the rotor in controlled ways, researchers can observe corresponding changes in the rate of time dilation. The measured response tracks velocity changes precisely, reinforcing the velocity-based interpretation. Laboratory rotation experiments also address potential concerns about reference frames. The laboratory frame attached to Earth is not strictly inertial due to Earth's rotation. However, The additional velocities introduced by laboratory rotation are much larger than variations due to Earth's rotation at a single location. Corrections for Earth's rotation are well understood and can be applied straightforwardly. Some experiments explicitly incorporate Earth's rotation into the analysis, treating the laboratory as a rotating frame itself. This allows separation of local rotational effects from global rotation effects and provides consistency checks across different reference frames. Precision clock experiments performed at institutions such as National Institute of Standards and Technology have pushed the sensitivity of laboratory tests to levels where even modest tangential velocities produce measurable time dilation. At this precision, velocity differences of a few meters per second sustained over hours can generate detectable effects. One conceptual outcome of laboratory tests is the demonstration that relativistic time dilation is local. It does not require extended travel or comparison between distant locations. A clock moved in a circle within a laboratory accumulates less proper time than an identical clock at rest nearby. This locality underscores the fundamental nature of the effect. These experiments also reinforce the operational definition of time. The clocks involved are compared directly. No interpretation based on signal delays or distant synchronization is required. The result is a straightforward comparison of accumulated clock readings. The precision of laboratory experiments allows detailed uncertainty analysis. Contributions from clock noise, environmental perturbations, rotation stability, and time transfer errors are quantified and minimized. In many cases, uncertainty budgets demonstrate that relativistic effects exceed experimental noise by comfortable margins. Rotating platform experiments complement other tests of time dilation by providing a regime where gravitational effects are suppressed and velocities are controlled precisely. Together with particle experiments, aircraft experiments, and satellite systems, they complete a comprehensive experimental picture. Another advantage of laboratory tests is reproducibility. Experiments can be repeated many times under nearly identical conditions, allowing systematic effects to be identified and corrected. This repeatability strengthens confidence in the conclusions. Laboratory velocity time dilation experiments also inform applied science. Technologies involving rotating systems, precision timing, and synchronization benefit from accurate modeling of relativistic effects, even at modest speeds. As clock precision continues to improve, these considerations become increasingly relevant. The cumulative evidence from rotating platforms and centrifuges confirms a central prediction of special relativity. Proper time depends on velocity. The effect appears in elementary particles, macroscopic clocks, aircraft, satellites, and laboratory rotors alike. Its manifestation in simple, local experiments underscores its universality. By demonstrating time dilation in settings where gravity is effectively constant, laboratory experiments isolate the kinematic core of relativity. They show that motion alone suffices to alter the passage of time as measured by clocks. These experiments complete the transition from theoretical prediction to routine measurement. Velocity-dependent time dilation is no longer a subtle effect inferred indirectly. It is a directly observed phenomenon accessible within the confines of a laboratory. Through careful control, precise measurement, and rigorous analysis, laboratory velocity time dilation experiments establish one of the most fundamental aspects of relativistic physics with clarity and confidence. Relativistic time transfer and synchronization address a fundamental experimental problem: how to compare clocks that are separated in space, moving relative to one another, and embedded in different gravitational potentials. Unlike experiments in which clocks are physically reunited, time transfer requires exchanging signals and correcting for propagation effects. At modern precision, these corrections are dominated by relativistic physics. Accurate synchronization therefore depends on a detailed operational treatment of signal delays, reference frames, and proper time evolution. At its core, time transfer converts local clock readings into a shared temporal description. Each clock measures its own proper time along its world line. To compare two clocks at different locations, One must map each proper time to a common coordinate time. This mapping is not implicit, it must be constructed using physical signals whose propagation obeys relativistic laws. Early synchronization methods relied on one-way signal transmission, where a clock at location A sends a time-stamped signal to location B. The receiving clock compares the received timestamp with its local reading. This method is insufficient at high precision because it requires prior knowledge of the signal's propagation delay. Any uncertainty in distance, propagation speed, or medium properties directly translates into timing error. Two-way time transfer overcomes this limitation by exchanging signals in both directions. In a basic two-way scheme, clock A sends a time-stamped signal to clock B, which immediately returns a response including its own timestamp. Clock A receives the return signal and computes the round-trip delay. Under the assumption of reciprocal propagation paths, the one-way delay can be inferred as half the round-trip delay, allowing the clocks to be synchronized. This reciprocity assumption is valid in many practical settings, but must be evaluated carefully. Motion, gravitational potential differences, and medium asymmetries can break exact reciprocity. Relativistic modeling is required to quantify these effects and apply appropriate corrections. Two-way time transfer using microwave signals has long been employed for comparing atomic clocks over continental and intercontinental distances. Satellite-based two-way methods allow ground clocks to be compared through relay satellites. In these systems, both clocks exchange signals via the satellite, and relativistic corrections are applied for satellite motion, gravitational potential, and signal propagation. Microwave time transfer benefits from mature technology and robustness under various weather conditions. However, its precision is limited by bandwidth, signal-to-noise ratio, and propagation effects in the atmosphere and ionosphere. At the nanosecond level and below, these effects require careful calibration and correction. Optical time transfer using laser links offers a significant improvement in precision. Optical frequencies are orders of magnitude higher than microwave frequencies, enabling finer temporal resolution. Laser-based time transfer can achieve picosecond level precision or better under favorable conditions. In optical two-way time transfer, laser pulses are exchanged between clocks through free space or optical fiber. The round-trip travel time is measured with high accuracy, and synchronization is achieved by accounting for known asymmetries. Optical links are particularly valuable for comparing state-of-the-art optical clocks whose intrinsic stability exceeds that of microwave-based transfer methods. Atmospheric propagation presents a challenge for free-space optical links. Variations in air density, temperature, and turbulence introduce fluctuations in signal delay. Adaptive optics, wavelength selection, and real-time delay estimation help mitigate these effects. In fiber-based links, environmental sensitivity manifests through temperature-induced length changes and mechanical strain. Active stabilization techniques are used to compensate for these variations. Relativistic effects enter time transfer at multiple levels. Signal propagation occurs along null paths in space-time, and the travel time depends on both geometry and gravitational potential. For Earth-based links, gravitational time delay effects associated with Earth's mass distribution contribute small but measurable corrections. These effects are well characterized and included in high-precision models. Motion introduces additional complications. When clocks move relative to one another, the timing of signal emission and reception must be described in a consistent reference frame. Relativistic Doppler shifts alter the frequency of received signals, and time dilation affects the rate at which clocks tick during the exchange. In satellite-based time transfer, these effects are substantial. Satellites move at several kilometers per second and experience different gravitational potentials than ground clocks. Signal delays depend on satellite position and velocity at the moments of transmission and reception. Accurate synchronization requires real-time orbital data and relativistic modeling. The reference frame used for time transfer must be defined explicitly. Common choices include Earth-centered inertial frames and Earth-fixed rotating frames. Transformations between these frames involve relativistic corrections related to Earth's rotation. Consistency requires that all clocks and signal paths be described within the same framework. One widely used approach defines a coordinate timescale tied to an Earth-centered inertial frame. Ground clocks and satellite clocks are related to this coordinate time through known relativistic transformations. Time transfer then becomes a problem of mapping proper times to coordinate time using measured signal delays. Relativistic corrections to signal delays include contributions from kinematic effects, gravitational potential differences, and path geometry. These corrections are computed using precise models of Earth's gravitational field, satellite orbits, and signal propagation paths. At modern precision, even small deviations from spherical symmetry in Earth's gravity can matter. Error analysis is central to time transfer experiments. Uncertainties arise from clock noise, signal detection jitter, propagation delay variations, and modeling inaccuracies. Each contribution must be quantified and minimized to achieve reliable synchronization. Continuous monitoring improves performance. By exchanging signals repeatedly over extended periods, statistical averaging reduces random noise. Systematic effects can be identified through correlation with environmental variables such as temperature, atmospheric conditions, or satellite geometry. Time transfer techniques are validated through closure tests. In a closure test, time is transferred from clock A to clock B, and then back to clock A through independent paths. Agreement between the original and return time provides a check on the consistency of the method and the adequacy of corrections. Modern time transfer supports comparisons between the most accurate clocks in the world. Institutions such as National Institute of Standards and Technology use advanced time transfer techniques to compare optical clocks separated by hundreds or thousands of kilometers. These comparisons enable the construction of international timescales and the evaluation of clock performance. Relativistic synchronization also plays a critical role in fundamental physics experiments. Tests of Lorentz invariance, measurements of gravitational redshift, and searches for temporal variations in fundamental constants all rely on precise time comparison between distant clocks. In these contexts, time transfer is part of the experimental apparatus. One important conceptual outcome of relativistic time transfer is the recognition that synchronization is not absolute. Synchronization depends on the chosen coordinate time and the procedures used to establish it. Proper time remains invariant, but comparisons require conventions and corrections grounded in physical modeling. Despite this dependence, relativistic time transfer achieves remarkable consistency. Independent methods using microwave links, optical links, and satellite relay converge on the same results when modeled correctly. This convergence provides confidence in both the experimental techniques and the underlying relativistic framework. The correction of signal delays illustrates the operational meaning of relativity. Time dilation and gravitational effects are not abstract concepts imposed after the fact. They are integral to predicting how signals propagate and how clocks compare. Omitting these effects leads to systematic errors that grow with distance, velocity, and time. As clock precision continues to improve, time transfer faces increasing demands. Effects once negligible become measurable. Modeling must incorporate finer details of Earth's gravity, atmospheric behavior, and relativistic kinematics. The success of current methods demonstrates that these challenges can be met through careful experiment and theory. Relativistic time transfer and synchronization thus form the connective tissue of modern timekeeping. They enable the comparison of clocks across space and motion, transforming isolated measurements of proper time into a coherent global time scale. Through two-way exchanges, laser links, microwave signals, and rigorous correction of delays, time transfer operationalizes relativity on a daily basis. It ensures that clocks separated by continents, moving at different speeds, and residing in different gravitational potentials can still be compared meaningfully. In doing so, it reinforces a central lesson of relativistic physics. Time is local, but comparison is possible through well-defined procedures grounded in the geometry of space-time. Systematic errors define the practical limits of experiments that measure relativistic time dilation. As clock precision improves, the dominant challenges shift from statistical noise to subtle physical influences that can bias measurements if not carefully controlled. Modern experiments therefore devote significant effort to identifying, characterizing, and suppressing non-relativistic effects so that the remaining signal can be confidently attributed to velocity-dependent time dilation. Thermal noise represents one of the most pervasive sources of systematic error in precision timing experiments. All clocks rely on physical processes whose frequencies depend, directly or indirectly, on temperature. In quartz oscillators, temperature alters the elastic properties of the crystal, shifting its resonance frequency. In atomic clocks, temperature affects blackbody radiation fields, atomic motion, and electronic energy levels. Even small temperature fluctuations can produce frequency shifts comparable to or larger than the relativistic effects under investigation. Modern experiments address thermal noise through a combination of passive and active control. Clocks are housed in temperature-stabilized enclosures with multilayer insulation and low thermal conductivity. Active feedback systems maintain temperature stability at the millikelvin level, or better. In optical clocks, blackbody radiation shifts are modeled quantitatively, and residual uncertainties are incorporated into the error budget. By maintaining identical thermal environments for moving and stationary clocks, experiments minimize differential thermal effects that could mimic time dilation. Vibration introduces another significant source of systematic error, particularly in experiments involving motion. Mechanical vibrations couple to clock components through several mechanisms. In quartz clocks, vibration alters crystal stress and orientation, directly affecting frequency. In atomic clocks, vibration can perturb microwave cavities, optical resonators, and trapping fields. Aircraft, rotating platforms, and centrifuges all generate vibration spectra that must be managed carefully. Isolation strategies include mechanical damping, vibration-absorbing mounts, and rigid structural design. Optical clocks often employ ultra-stable optical cavities mounted in vibration-insensitive geometries. Real-time vibration monitoring allows correlation between clock frequency fluctuations and measured acceleration, enabling post-processing corrections. In some experiments, clock comparisons are performed continuously during motion, allowing vibration-induced effects to be distinguished from steady relativistic offsets. Magnetic fields influence clock behavior through the Zeeman effect, which shifts atomic energy levels in the presence of magnetic fields. Cesium clocks, hydrogen masers, and optical clocks all exhibit magnetic sensitivity, though to varying degrees. Environmental magnetic fields arise from Earth's field, electrical equipment, and moving ferromagnetic materials. In experiments involving rotation or transport, changes in orientation relative to Earth's magnetic field can introduce frequency shifts. Mitigation strategies involve magnetic shielding and field control. Clocks are enclosed within layers of high permeability materials that attenuate external magnetic fields. Internal coils generate controlled bias fields, stabilizing the atomic transition frequency and reducing sensitivity to external variations. Residual magnetic sensitivity is measured experimentally and included in uncertainty estimates. By ensuring that moving and reference clocks experience similar magnetic environments, differential magnetic effects are minimized. Gravitational gradients pose a subtle challenge in experiments designed to isolate velocity effects. Even small differences in altitude correspond to measurable differences in gravitational potential at modern clock precision. In laboratory experiments, clocks separated vertically by centimeters or even millimeters can experience detectable gravitational time dilation. In aircraft or rotating platform experiments, vertical motion and structural flexing can introduce unintended gravitational contributions. To isolate pure velocity time dilation, experiments are designed to keep clocks at the same average gravitational potential. In rotating platform experiments, clocks are placed at the same height relative to Earth's surface, differing only in tangential velocity. In aircraft experiments focused on velocity effects, altitude profiles are carefully controlled or modelled so that gravitational contributions can be subtracted accurately. Gravitational gradients also arise from local mass distributions. Nearby buildings, geological structures, and even large experimental apparatus can influence the local gravitational potential. At the highest levels of precision, these effects become relevant. Modern experiments use detailed gravitational models and, in some cases, gravimetric measurements to account for local variations. Another systematic concern involves clock synchronization and time transfer. Comparing clocks during or after motion requires transferring time information through signals that themselves experience relativistic effects. Signal delays depend on path length, propagation medium, and relative motion. Any unmodelled asymmetry in signal paths can introduce timing errors. Two-way time transfer techniques reduce sensitivity to such asymmetries by measuring round-trip delays. Optical fiber links and free-space laser links provide high-precision transfer with active delay stabilization. Remaining uncertainties are characterized through calibration experiments and closure tests. By ensuring that time transfer errors are smaller than the expected relativistic signal, experiments maintain confidence in their conclusions. Clock drift and aging contribute long-term systematic effects. Even the most stable clocks exhibit slow frequency changes over time due to material relaxation, component aging, or gradual environmental changes. In experiments lasting hours or days, these drifts can accumulate into significant timing offsets. Drift is managed through pre- and post-experiment calibration, ensemble averaging, and differential comparison. Using multiple clocks allows common mode drift to be identified and removed. Continuous comparison during experiments enables separation of steady relativistic offsets from slow drift trends. Statistical methods play a key role in quantifying residual uncertainty. Acceleration effects merit careful consideration. Clocks subjected to acceleration experience forces that can influence their physical structure. Classical intuition might suggest that acceleration directly alters clock rates. Relativistic theory predicts that proper time depends on velocity rather than acceleration itself. Experimental evidence supports this prediction, but acceleration-induced mechanical effects must still be controlled. In rotating systems, centrifugal forces act continuously on clocks. Structural deformation under load can alter clock components, producing frequency shifts unrelated to relativity. Experimental designs minimize these effects through rigid construction, symmetric mounting, and operation within mechanical limits. By varying rotation speed and comparing results, researchers verify that observed time dilation scales with velocity rather than with applied force. Environmental electromagnetic noise introduces additional complexity. Radio frequency interference, power supply fluctuations, and electronic crosstalk can affect clock electronics and signal processing. Shielding, filtering, and redundant measurement channels reduce susceptibility to such noise. Monitoring environmental parameters allows correlation analysis to identify and mitigate interference. Modern experiments emphasize redundancy and cross-validation. Multiple clocks of different types are often used simultaneously. Agreement between clocks based on different physical principles strengthens confidence that observed effects are genuinely relativistic. Discrepancies prompt investigation into systematic influences rather than reinterpretation of theory. Uncertainty budgets provide a structured framework for evaluating experimental limits. Each potential error source is quantified, either through direct measurement or conservative estimation. Contributions are combined using statistical methods to yield a total uncertainty. Relativistic effects are considered confirmed when measured offsets exceed combined uncertainty by a clear margin. As clock precision improves, new systematic effects emerge. Phenomena once negligible become measurable. For example, relativistic coupling between rotation and gravity, tidal gravitational variations due to the Moon and Sun, and relativistic effects associated with Earth's non-spherical shape all enter high-precision analyses. These effects are modelled using established physical theory and incorporated into experimental predictions. The isolation of pure velocity effects therefore becomes an exercise in subtraction. Measured time differences include contributions from velocity, gravity, environment, and instrumentation. Each non-kinematic contribution is either minimized by design or calculated and removed. The residual signal is then compared with the velocity-dependent prediction of special relativity. This approach transforms potential limitations into opportunities. By modelling and correcting systematic effects accurately, experiments test not only special relativity, but also general relativity, geophysics, and environmental physics. Precision timekeeping becomes a probe of multiple physical domains simultaneously. The success of modern experiments in isolating velocity-time dilation reflects decades of technological and methodological refinement. Advances in materials science, control systems, data analysis, and theoretical modelling all contribute. What once required large-scale experiments and long durations can now be achieved in compact setups over short times. Systematic errors thus define the frontier rather than the obstacle. They set the scale at which new physics might appear, while their careful control confirms the robustness of existing theory. In the context of time dilation, the ability to isolate pure velocity effects across diverse experimental platforms demonstrates the predictive power and internal consistency of relativistic physics. By confronting and overcoming thermal noise, vibration, magnetic fields, gravitational gradients, and synchronization limits, modern experiments achieve a clear separation between relativistic effects and experimental artifacts. The resulting measurements stand among the most precise and reliable confirmations of fundamental physical principles. Extreme velocity regimes extend experimental tests of relativistic time dilation beyond terrestrial motion and conventional accelerators, targeting conditions where velocities, durations, or coherence reach new limits. Future experiments focus on three complementary directions: clocks carried by fast spacecraft, clocks embedded within particle beams, and next-generation optical lattice clocks whose precision makes even modest velocities yield large, measurable effects. Together, these approaches probe relativistic predictions across regimes that differ in scale, environment, and methodology while maintaining a common operational core: the comparison of proper time accumulated along distinct world lines. Fast spacecraft provide a natural pathway to sustained relativistic motion over long durations. While orbital velocities around Earth already generate measurable effects, interplanetary trajectories and deep space missions enable higher speeds, longer integration times, and cleaner dynamical environments. Spacecraft on solar-centric orbits experience velocities that vary substantially with heliocentric distance. Proper time accumulation along such trajectories can be predicted with high fidelity using well-characterized gravitational models and precise navigation data. The experimental objective is to carry clocks whose stability exceeds the uncertainty in trajectory reconstruction so that measured time offsets test relativistic integrals rather than instrumentation limits. Near-term concepts emphasize placing state-of-the-art optical clocks aboard spacecraft designed explicitly for timekeeping experiments. Optical lattice clocks based on neutral atoms such as strontium or ytterbium offer fractional uncertainties approaching 1 part in 10 to the 18th. In space, the absence of seismic noise and the potential for thermally stable platforms improve clock performance further. The dominant challenges shift to radiation hardness, long-term autonomy, and robust time transfer between spacecraft and ground stations. Time transfer for deep space clock experiments requires bidirectional optical links capable of maintaining phase coherence over very long distances. Laser ranging and coherent optical communication provide the technological foundation. Two-way exchanges mitigate path delay uncertainties and allow relativistic corrections to be applied symmetrically. Accurate ephemerides and onboard inertial measurements supply the kinematic inputs required to compute expected proper time differences. Agreement between measured and predicted offsets over months or years would constitute a stringent test of time dilation under continuously varying velocities. More ambitious mission concepts propose exploiting gravity assists to reach higher heliocentric speeds. Flybys of planets increase spacecraft velocity relative to the Sun, amplifying kinematic time dilation while maintaining precise tracking. The resulting proper time signature is distinctive and calculable. Maintaining clock performance through rapidly changing thermal and radiation environments during close planetary encounters remains the primary technical challenge. Solar probe trajectories and interstellar precursor missions push velocities further. Spacecraft approaching close to the Sun can reach tens of kilometers per second. Although still far below relativistic speeds in absolute terms, the combination of high velocity and long integration time yields measurable relativistic accumulation. In these regimes, separating kinematic effects from gravitational contributions becomes a matter of precision modeling rather than sensitivity. The experiment tests whether measured time follows the predicted space-time path length when all known influences are included. Particle beams with embedded clocks represent a conceptually distinct extreme. Instead of carrying macroscopic clocks through space, these experiments embed clock-like degrees of freedom within relativistic particles themselves. The operational definition remains consistent. A periodic internal process functions as a clock whose evolution follows proper time. The novelty lies in controlling and reading out that process while the particle moves at near light speed. One approach uses spin precession as a clock. Charged particles circulating in storage rings exhibit spin dynamics governed by well-characterized electromagnetic interactions. The accumulated spin phase depends on proper time and can be measured with high precision using polarimetry. By controlling beam energy and monitoring spin evolution over many revolutions, experiments effectively measure time dilation via phase accumulation rather than decay statistics. This approach benefits from long coherence times and repeated sampling. Another approach proposes embedding bound systems, such as ions or exotic atoms, within relativistic beams. Internal transition frequencies provide clock signals whose evolution tracks proper time, measuring frequency shifts or accumulated phase, while the system circulates in a ring, tests time dilation in regimes where Lorentz factors reach thousands. Practical challenges include maintaining coherence in high radiation environments and achieving reliable readout without perturbing the system. Storage rings at facilities such as CERN provide natural platforms for such experiments. High-energy beams, stable magnetic optics, and sophisticated diagnostics enable precise control of particle trajectories and energies. Embedding clock degrees of freedom within beams leverages existing infrastructure while extending experimental reach. The principal limitation is decoherence induced by electromagnetic noise and interactions with residual gas, which constrains integration time. A complementary strategy extends earlier lifetime measurements into new regimes. Unstable particles function as statistical clocks whose decay rates track proper time. Increasing beam energy increases the Lorentz factor, stretching lifetimes proportionally. Measuring deviations from the expected scaling tests both relativistic time dilation and potential new physics at high gamma. The experimental frontier lies in improving control over systematics to distinguish subtle effects beyond the leading relativistic term. Next-generation optical lattice clocks transform the experimental landscape even without extreme velocities. Their precision makes time dilation observable at velocities of meters per second over laboratory timescales. This sensitivity opens experiments that combine modest motion with exceptional control, effectively trading speed for precision. Optical lattice clocks trap thousands of atoms in periodic potentials formed by laser light, suppressing motion-induced frequency shifts while enabling long interrogation times. Advances in laser coherence, cavity stability, and atomic control continue to reduce noise. Transportable versions allow clocks to be moved along prescribed paths, on vehicles, aircraft, or rotating platforms, while maintaining near-laboratory performance. The accumulated proper time difference between trajectories can be resolved with high confidence. Future experiments envision networks of optical clocks connected by stabilized optical fibers and free-space optical links. By moving one clock through a controlled velocity profile while others remain stationary, researchers can map the dependence of accumulated proper time on velocity with fine resolution. The predicted proper time integral becomes the central observable, and deviations from prediction would signal either unaccounted systematics or new physics. A key advantage of optical lattice clocks is universality across atomic species. Different transitions provide independent realizations of time. Agreement among species under identical motion tests whether time dilation is truly mechanism independent at unprecedented precision. Any discrepancy would prompt scrutiny of experimental assumptions and theoretical foundations. Future programs also aim to combine velocity and gravity in controlled ways. Clocks carried on vertical trajectories, elliptical orbits, or variable speed platforms sample world lines that traverse different space-time regions. Proper time differences predicted by relativistic theory incorporate both kinematic and gravitational terms. High-precision clocks allow these contributions to be separated and tested simultaneously. Time transfer remains an enabling technology. Optical two-way links with active stabilization must operate reliably across moving platforms and long distances. Improvements in adaptive optics, wavelength multiplexing, and real-time delay estimation are essential. Closure tests and redundant paths ensure that synchronization errors remain well below the relativistic signals of interest. Uncertainty budgets for future experiments emphasize modeling accuracy. As clock noise diminishes, uncertainties in trajectory reconstruction, gravitational potential, and environmental coupling dominate. High-fidelity inertial navigation, gravimetric mapping, and environmental monitoring become integral components of time dilation experiments. The task shifts from sensitivity to comprehensive accounting. Theoretical modeling must keep pace with experimental precision. At extreme accuracy, higher-order relativistic terms, coupling between motion and gravity and tidal effects contribute measurably. Predictions require consistent reference frames and careful treatment of non-inertial motion. The reward is a framework where theory and experiment meet at levels that probe the structure of space-time with unprecedented clarity. Institutional efforts reflect this convergence. Programs at organizations such as European Space Agency and NASA integrate precision timekeeping into mission planning, navigation, and fundamental physics objectives. Dedicated timekeeping missions are under study, combining optical clocks, laser links, and deep space trajectories to probe relativistic predictions beyond Earth-bound experiments. Long-term visions include relativistic clocks aboard fast solar sail spacecraft or missions using advanced propulsion concepts. Even modest increases in velocity sustained over years yield large proper time separations. These experiments emphasize stability and continuity over peak speed, aligning with the strengths of optical clocks. Across all approaches, a unifying theme persists. Time dilation is tested by comparing accumulated proper time along known paths. Whether the clock is a macroscopic device on a spacecraft, a quantum degree of freedom in a particle beam, or an ensemble of atoms in an optical lattice, the measurement reduces to the same operational comparison. Extreme velocity regimes and future experiments thus extend the empirical reach of relativity without altering its conceptual foundation. They replace indirect inference with direct integration and short demonstrations with long-duration accumulation. As precision improves, experiments transition from confirming leading-order predictions to probing corrections and limits. The outcome is a mature experimental program in which time dilation is not only verified but mapped across scales. Spacecraft trajectories, particle beams, and optical lattices become complementary tools for tracing space-time geometry through timekeeping. Continued agreement between prediction and measurement across these regimes would further cement time dilation as one of the most robust features of modern physics, while any deviation would point unambiguously toward new phenomena. Experiments on time dilation establish a precise and limited set of empirical claims about how time behaves in physical systems. These claims are grounded in direct measurement, reproducible across platforms, and quantitatively predictable. At the same time, experiments also delineate what time dilation does not assert. Understanding this boundary between confirmed physics and speculative interpretation is essential for evaluating the strength and meaning of relativistic time dilation. The core empirical result confirmed by experiments is that the elapsed time measured by a clock depends on the clock's world line through space-time. When two identical clocks follow different trajectories, differing in velocity, gravitational potential, or both, and are later compared, they generally record different amounts of elapsed time. This difference is not inferred indirectly. It is measured by direct clock comparison, particle decay statistics, phase accumulation, or frequency shifts. The result holds across a vast range of physical realizations. Experiments confirm that time dilation is quantitative, not qualitative. The magnitude of the effect matches precise mathematical predictions derived from relativistic theory. In special relativity, the dependence on velocity is captured by the Lorentz factor. In general relativity, gravitational potential contributes additional calculable terms. Across particle experiments, aircraft flights, satellite systems, laboratory rotors, and optical clock comparisons, the measured offsets agree with predicted values within experimental uncertainty. This agreement is not limited to a single regime or method. Time dilation has been confirmed using unstable particles whose decay rates serve as clocks, atomic transitions in cesium and optical clocks, spin precession in relativistic beams, and synchronized clock networks spanning continents and space. The diversity of experimental platforms strengthens the conclusion that time dilation is not an artifact of any particular mechanism. Another experimentally confirmed feature is universality. Different clocks, mechanical, atomic, optical, quantum, and statistical, exhibit the same relativistic behavior when subjected to the same motion and gravitational conditions. Experiments do not reveal dependence on clock composition, size, internal structure, or operating principle once known environmental effects are controlled. This universality indicates that time dilation reflects space-time geometry rather than device-specific physics. Experiments also confirm that time dilation depends on velocity and gravitational potential, not on acceleration itself. Clocks undergoing sustained acceleration in circular motion exhibit time dilation consistent with their instantaneous velocity. No additional dilation proportional to acceleration alone has been observed. This conclusion emerges from storage ring experiments, rotating platforms, and centrifuges where acceleration is large and continuous, but the observed effect tracks velocity precisely. Another confirmed aspect concerns proper time. Experiments consistently show that the time measured by a clock corresponds to the invariant proper time along its trajectory. Different observers may assign different coordinate times to the same events, but all observers agree on the proper time accumulated by the clock. This invariance has been verified operationally by reuniting clocks after different paths and by comparing decay processes across frames. Time dilation experiments also confirm the relativity of simultaneity as an operational consequence, not as a metaphysical statement. Synchronization procedures based on signal exchange yield frame-dependent simultaneity. and this dependence is required for internal consistency of time dilation measurements. Experiments involving time transfer and synchronization validate the predictions associated with these procedures at high precision. The empirical scope of these confirmations is broad in velocity and precision. Particle experiments probe Lorentz factors reaching thousands. Satellite systems operate continuously over decades. Optical clocks resolve effects at the level of centimeters of height difference and meters per second of velocity. Across this range, no systematic deviation from relativistic predictions has been observed within experimental limits. Equally important is what experiments do not confirm. Experiments do not establish that time itself flows differently in any subjective or experiential sense. Time dilation is a statement about clock readings and physical processes, not about consciousness or perception. Physics remains silent on experiential time, and experiments neither address nor resolve such questions. Experiments also do not imply that time is an illusion or that temporal order is arbitrary. Causality remains intact. Events connected by cause and effect maintain their order in all frames. Time dilation alters rates of processes, not causal structure. No experiment has observed violations of causality arising from relativistic time dilation. Another common misinterpretation concerns symmetry. Experiments confirm that time dilation is frame-dependent, but not contradictory. Different observers describe time intervals differently using their own coordinates, yet all agree on measurable outcomes when clocks are compared directly. Experiments do not support the notion that each observer is equally right in an unconstrained sense. Predictions must be made within a specified reference frame, and experiments verify those predictions consistently. Time dilation experiments also do not validate speculative extensions that go beyond tested regimes. Claims involving hypothetical violations of Lorentz invariance, exotic space-time structures, or observer-dependent realities lie outside the confirmed experimental domain unless supported by direct measurement. Precision experiments place increasingly tight bounds on such deviations, but absence of evidence remains distinct from evidence of absence. Another limit concerns quantum interpretations. While quantum systems obey relativistic time dilation in their evolution, experiments do not resolve deeper interpretive questions about time in quantum mechanics. Time dilation constrains how quantum phases evolve along trajectories, but it does not answer questions about measurement, collapse, or the nature of quantum time. Experiments also do not require or confirm any particular philosophical interpretation of space-time. Minkowski space-time geometry provides an effective mathematical framework, but experiments test predictions, not metaphysical commitments. Competing interpretations that yield identical predictions remain experimentally indistinguishable. What elevates time dilation to one of the most experimentally secure effects in physics is the redundancy of confirmation. The same mathematical structure predicts outcomes in systems that differ by orders of magnitude in scale, energy, and composition. Failures would be conspicuous and cumulative. Instead, consistency persists. Another factor is predictive necessity. Time dilation is not merely observed after the fact. It is required for technologies to function. Satellite navigation systems depend on relativistic corrections continuously. High-energy accelerator experiments require time dilation for correct interpretation of decay rates. Precision timekeeping networks incorporate relativistic modeling by design. The success of these systems constitutes ongoing experimental validation. Time dilation also benefits from direct measurability. Many fundamental effects in physics are inferred indirectly or through complex modeling. Time dilation can be measured by comparing clocks before and after controlled motion. This simplicity reduces interpretive ambiguity and strengthens evidential weight. Error analysis further reinforces confidence. Modern experiments quantify thermal, vibrational, electromagnetic, gravitational, and synchronization effects with precision. Independent experiments using different methods converge on the same results. Residual discrepancies fall within known uncertainty budgets rather than pointing toward unmodeled physics. Theoretical flexibility also plays a role. Relativistic time dilation emerges from minimal assumptions, invariance of physical law across inertial frames, and a finite, invariant signal speed. Experiments test the consequences of these assumptions directly. Alternative theories that reproduce the same predictions remain viable, but any theory that contradicts observed time dilation is ruled out empirically. Importantly, time dilation experiments confirm relationships, not narratives. They confirm how elapsed time relates to motion and gravity. They do not privilege one observer's experience over another's, nor do they assert that time is slower in an absolute sense. They establish operational facts that can be used reliably in calculation and technology. The experimental security of time dilation also stems from historical continuity. Early conceptual reasoning predicted effects later confirmed by particle experiments. Transported clock experiments bridged theory and macroscopic measurement. Satellite systems institutionalized relativistic corrections. Optical clocks now probe the same relationships with unprecedented resolution. Each stage reinforced rather than revised the core predictions. In physics, few effects enjoy such comprehensive validation across methods and scales. Time dilation stands alongside conservation laws and quantum energy quantization as a phenomenon whose empirical foundation is both deep and broad. The experiments confirm that time, as measured by clocks, is not universal across all trajectories. They confirm that this non-universality follows precise, testable rules. They confirm that these rules apply everywhere they have been tested. They do not confirm speculative meanings beyond those rules. They do not resolve philosophical debates about the nature of time. They do not imply dramatic reinterpretations of reality beyond what measurement supports. This clarity is a strength rather than a limitation. By drawing a sharp boundary between what is measured and what is inferred, time dilation remains one of the most reliable tools in modern physics. Through decades of increasingly precise experimentation, time dilation has moved from a counterintuitive prediction to an operationally indispensable fact. Its confirmation rests not on a single dramatic test, but on a dense network of mutually reinforcing measurements. That network is what makes relativistic time dilation one of the most experimentally secure effects in all of physics.